Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into one of the most intriguing astronomical mysteries of recent years, the story of 3I Atlas, a mysterious visitor from another star system that challenged everything scientists thought they knew about interstellar objects. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The stranger that arrived in 2019 emerges from the darkness of interstellar space as 3I Atlas becomes only the third confirmed interstellar object detected passing through our solar system, following a trajectory that mathematical analysis proves originated from beyond the sun's gravitational influence and the familiar realm of planets, asteroids, and comets that have orbited our star for billions of years. This cosmic wanderer represents a messenger from distant stellar neighborhoods, carrying with it the chemical signatures and physical characteristics that developed around alien suns in stellar systems that may have formed under completely different conditions than our own solar system. Interstellar object identification requires precise mathematical analysis of orbital characteristics, where astronomers must demonstrate that an object's trajectory exhibits hyperbolic geometry with eccentricity values exceeding unity, indicating velocities that surpass the solar system's gravitational escape threshold. Only objects that achieve these extreme orbital parameters can be confirmed as genuine visitors from interstellar space rather than solar system natives, following unusual but bound elliptical orbits. The mathematical precision required for this determination involves complex gravitational calculations that account for planetary perturbations and solar radiation pressure effects that might alter apparent trajectories. Discovery circumstances for 3I Atlas reflect the systematic astronomical survey programs that monitor the sky for potentially hazardous asteroids and unusual objects, where automated telescopes continuously scan celestial coordinates and identify moving objects through systematic comparison of sequential images taken hours or days apart. The Asteroid Terrestrial Impact Last Alert System Atlas telescope network, designed primarily for planetary defense purposes, detected this interstellar visitor through the same observational protocols used to identify potentially dangerous near-Earth asteroids, demonstrating how astronomical surveys often make unexpected discoveries. Only took astronomical analysis approximately weeks to confirm 3I Atlas as an interstellar object through orbital determination processes that required multiple observations and complex mathematical modeling to distinguish interstellar trajectories from highly elliptical solar system orbits. Only required systematic observation and orbital calculation to establish the object's hyperbolic trajectory and confirm its origin from beyond the solar system's gravitational boundary. Only needed precise astrometric measurements to determine that this cosmic visitor carried sufficient velocity to escape solar gravitational influence and continue its journey toward other stellar systems. Physical characteristics of 3I Atlas remain partially mysterious due to observational limitations imposed by the object's small size, great distance, and rapid motion through the inner solar system, creating measurement challenges that prevent definitive determination of properties like exact dimensions, surface composition, rotation period, and internal structure. These observational constraints reflect fundamental limitations in current astronomical instrumentation when applied to small, distant objects moving at high velocities through solar system space. The mystery of interstellar object frequency involves understanding how often such visitors pass through our solar system and what fraction of interstellar objects remain undetected due to observational limitations, small size, or trajectories that don't bring them close enough to Earth for easy detection. Statistical analysis suggests that interstellar objects may pass through the solar system relatively frequently, perhaps several times per year, but most go unnoticed due to their small size and the limited coverage of current astronomical survey programs. Chemical composition analysis of 3I Atlas relies on spectroscopic observations that measure reflected and emitted light to determine surface mineral composition and compare these signatures with known asteroid and comet materials from our solar system. These spectroscopic studies provide the primary method for understanding what interstellar objects are made of and how their compositions might differ from solar system materials that formed under local stellar conditions. Velocity analysis reveals that 3I Atlas approached the solar system with speeds indicating acceleration by gravitational interaction with stellar systems located many light years from our Sun, suggesting a complex gravitational history that may have involved multiple stellar encounters during its journey through interstellar space. The object's velocity vector provides clues about its possible origin direction and the stellar systems that may have influenced its trajectory during its million-year journey between stars. Size estimation challenges arise from the difficulty in distinguishing between object size and surface reflectivity when analyzing brightness measurements, as a small, highly reflective object can appear identical to a larger dark object when observed from great distances. This size albedo degeneracy creates uncertainty in fundamental physical properties while requiring additional observational techniques or assumptions to resolve basic questions about the object's dimensions. Rotation characteristics of 3I Atlas exhibit variations in brightness that suggest either irregular shape, variable surface composition, or complex rotation patterns that create systematic changes in reflected light as different surface areas become visible from Earth's perspective. These brightness variations provide information about the object's physical properties while creating observational opportunities to study surface characteristics and rotation dynamics. Thermal properties analysis through infrared observations attempts to measure heat emission from 3I Atlas to determine surface temperature and thermal characteristics that provide information about composition, size, and thermal history during its approach to the Sun. These thermal measurements supplement visible light observations while providing additional constraints on physical properties and composition hypotheses. Observational window limitations create time pressure for astronomical studies, as 3I Atlas follows its hyperbolic trajectory away from the inner solar system, providing only a brief opportunity for detailed observation before the object becomes too faint and distant for further study with current telescopes. This limited observational window emphasizes the importance of rapid response and coordinated international observational campaigns when interstellar objects are detected. Comparative planetology applications use 3I Atlas observations to understand planetary formation processes around other stars by analyzing the physical and chemical characteristics of material that was likely ejected from alien planetary systems during their formation or evolution. These comparative studies provide insights into how planetary formation might vary between different stellar environments, while offering glimpses of planetary system development under conditions that differ from solar system formation. Technological implications of 3I Atlas detection highlight both the capabilities and limitations of current astronomical survey systems, while motivating development of improved detection methods and space-based missions designed to study interstellar objects during their brief passages through the solar system. The detection success demonstrates existing survey capabilities while revealing opportunities for enhanced astronomical monitoring systems. International collaboration requirements for 3i Atlas research involve coordinating observations from multiple telescopes worldwide to maximize data collection during the limited time window available for study, demonstrating how interstellar object research requires global astronomical cooperation and rapid data sharing to achieve comprehensive characterization of these rare cosmic visitors. Modern astronomical techniques enable systematic detection and characterization of interstellar objects through automated survey systems, advanced orbital analysis methods, and sophisticated spectroscopic analysis that provide unprecedented capabilities for studying visitors from other stellar systems. Contemporary astronomical capabilities continue improving while enabling more detailed study of interstellar objects and better understanding of their origin and characteristics. Tonight, every point of light moving across the night sky, every systematic astronomical survey searching for cosmic visitors, every mathematical analysis that distinguishes interstellar trajectories from solar system orbits carries forward the legacy of 3i Atlas and the ongoing human quest to understand the cosmic neighborhood through direct study of material that originated around distant stars, bringing fragments of alien worlds within reach of terrestrial telescopes and human curiosity. A name that tells a story unfolds through the systematic nomenclature of astronomical discovery, where the designation 3i Atlas encodes precise information about detection sequence, classification category, and discovery circumstances that enable astronomers worldwide to understand fundamental characteristics of this cosmic visitor through standardized naming conventions established by the International Astronomical Union. The prefix 3i indicates that this object represents the third confirmed interstellar visitor detected passing through our solar system, following the revolutionary first detection of 1 Oumuamua in 2017 and the subsequent discovery of 2i Borisov in 2019, creating a systematic catalogue of confirmed visitors from beyond our stellar neighbourhood. Astronomical naming conventions operate through systematic protocols that encode discovery information, orbital characteristics, and object classification within standardized designations that enable scientific communication and prevent confusion between different astronomical objects. The interstellar designation I distinguishes these objects from traditional comet and asteroid classifications, while sequential numbering provides systematic identification that reflects discovery chronology and enables tracking of interstellar object detection frequency over time. Atlas Telescope Network Identification reflects the Asteroid Terrestrial Impact Last Alert System, a sophisticated astronomical survey program designed primarily for planetary defense applications through systematic monitoring of near-Earth space for potentially hazardous asteroids and comets that might pose impact threats to Earth. This survey system operates through multiple telescope stations positioned globally to provide continuous sky coverage and automated detection of moving objects through systematic image comparison and analysis. Only took the Atlas survey system approximately hours to days to identify 3i Atlas as an unusual object through automated detection algorithms that flag moving objects with anomalous characteristics, including brightness variations, trajectory parameters, or velocity measurements that differ from typical near-Earth asteroid and comet populations, only required systematic follow-up observations to confirm the object's hyperbolic trajectory and establish its interstellar origin through precise astrometric measurements and orbital determination calculations. only needed international astronomical collaboration to verify initial observations and confirm the object's classification as a genuine interstellar visitor. Discovery timeline documentation preserves detailed records of observation circumstances, telescope configurations, atmospheric conditions, and measurement parameters that enable subsequent researchers to understand detection limitations and observational constraints that affected initial characterization of 3I Atlas. These discovery records provide essential context for interpreting subsequent observations, while establishing baseline measurements for comparative analysis with future interstellar object detections. The mystery of detection bias involves understanding how current astronomical survey systems might systematically miss certain types of interstellar objects due to size limitations, brightness constraints, trajectory orientations, or timing factors that prevent detection of objects that might provide different insights into interstellar populations and formation mechanisms. This detection bias affects statistical interpretation of interstellar object frequency and characteristics while highlighting observational limitations that influence scientific understanding. Nomenclature evolution reflects changing astronomical understanding as interstellar objects transition from theoretical possibilities to observed realities, requiring development of new classification systems and naming conventions that accommodate objects whose properties and origins differ fundamentally from traditional solar system populations. These nomenclature changes demonstrate evolving scientific frameworks while establishing systematic approaches for categorizing cosmic visitors from beyond the solar system. International coordination requirements for interstellar object confirmation involve systematic verification procedures that require multiple independent observations from different astronomical facilities to establish orbital parameters and confirm interstellar classification through redundant measurements and cross-validation of trajectory calculations. This international coordination ensures scientific rigor while preventing false positive identifications that might compromise interstellar object catalogues. Catalog maintenance systems preserve systematic records of confirmed interstellar objects along with detailed observation histories, orbital parameters, physical characteristics, and discovery circumstances that enable comparative analysis and statistical interpretation of interstellar visitor populations. These catalogues provide essential databases for understanding interstellar object frequency, characteristics, and origin, while supporting continued research into visitors from other stellar systems. Discovery announcement protocols operate through systematic communication channels that notify the global astronomical community about new interstellar object detections, while providing preliminary orbital parameters and observation opportunities that enable coordinated follow-up studies during limited observational windows. These announcement systems facilitate rapid scientific response while maximizing data collection opportunities for rare interstellar visitors. Follow-up observation coordination involves systematic scheduling of telescope time and observational resources to maximize data collection from multiple facilities during the brief period when interstellar objects remain accessible for detailed study before continuing their journeys beyond the solar system. This coordination requires international cooperation and flexible scheduling to accommodate unexpected discoveries and rapidly changing observational opportunities. Database integration ensures that 3I Atlas observations become incorporated into systematic astronomical databases that support comparative studies, statistical analysis, and theoretical modeling of interstellar object populations, while providing standardized data formats that enable efficient scientific research and collaboration. These database systems preserve observational data while facilitating ongoing research into interstellar visitors and their characteristics. Publication standards for interstellar object research require systematic documentation of discovery circumstances, observational methods, measurement uncertainties, and analysis procedures that enable scientific peer review and validation of interstellar object claims, while establishing credible scientific records for future research applications. These publication standards ensure scientific rigor, while facilitating knowledge transfer and collaborative research. Archive preservation systems maintain long-term storage of 3I Atlas observational data, including raw telescope images, processed measurements, and analysis results that enable future reanalysis with improved techniques and support continued research into interstellar object characteristics and origins. These archive systems preserve irreplaceable observational data while supporting evolving scientific understanding and technological capabilities. Educational applications of 3I Atlas nomenclature provide systematic examples of astronomical naming conventions and discovery processes that demonstrate how scientific classification systems evolve to accommodate new phenomena while maintaining systematic organization that supports scientific communication and research. These educational applications promote scientific literacy while illustrating systematic approaches to astronomical discovery and classification. Historical significance of 3I Atlas within the emerging field of interstellar object astronomy establishes important precedents for detection methods, observational strategies, and classification procedures that guide future research into cosmic visitors from beyond the solar system. The object's discovery and study contribute to developing systematic frameworks for interstellar object research while advancing understanding of galactic material exchange processes. Future naming conventions for interstellar objects may evolve based on lessons learned from early detections like 3I Atlas, potentially incorporating additional information about origin, composition, or trajectory characteristics that provide more detailed scientific information within standardized designations. These evolving conventions reflect advancing scientific understanding while maintaining systematic organization that supports efficient scientific communication and research. Modern astronomical surveys continue expanding detection capabilities for interstellar objects through improved telescope technology, enhanced automated detection algorithms, and systematic monitoring programs that increase the probability of detecting future cosmic visitors like 3I Atlas, while providing better characterization of interstellar object populations and their scientific significance. Tonight, every systematic astronomical survey scanning the night sky, every standardized naming convention that organizes scientific knowledge, every coordination protocol that enables international scientific collaboration carries forward the legacy of 3I Atlas and the systematic approach to astronomical discovery that transforms isolated observations into comprehensive understanding of cosmic phenomena that connect our solar system with the broader galactic community. The hyperbolic path of an outsider traces through space according to mathematical principles that distinguish interstellar visitors from solar system natives through orbital geometry that defies the elliptical trajectories governing planets, asteroids, and comets bound to our Sun's gravitational influence. When 3I Atlas follows an extreme hyperbolic orbit with an eccentricity significantly greater than 1, this mathematical signature provides definitive proof that the object originated from interstellar space rather than forming within our solar system, as only objects carrying sufficient kinetic energy from external gravitational acceleration can achieve the velocities necessary to maintain hyperbolic trajectories through solar gravitational fields. Orbital eccentricity measurements operate through precise mathematical relationships, where eccentricity values between 0 and 1 indicate bound elliptical orbits characteristic of solar system objects, while eccentricity values exceeding unity demonstrate unbound hyperbolic trajectories that can only result from objects entering the solar system with velocities exceeding local escape speed. The eccentricity of 3I Atlas measures approximately 4.2, a value so extreme that it eliminates any possibility of solar system origin, while indicating approach velocities that required gravitational acceleration by stellar systems located many light-years from our Sun. Gravitational dynamics governing hyperbolic trajectories follow Newton's laws of motion and universal gravitation, where objects approaching the solar system from interstellar space experience systematic gravitational acceleration as they fall toward the Sun, reach maximum velocity at perihelion passage, then decelerate as they climb back out of the solar gravitational well, while following precise mathematical curves that conserve energy and angular momentum throughout their solar system passage. These gravitational mechanics operate with clockwork precision regardless of object composition or origin. Only took 3I Atlas approximately 2 years to traverse the inner solar system from its detection beyond Mars' orbit to its passage beyond Earth's orbit, while following its predetermined hyperbolic path that brought it within approximately 0.25 astronomical units of the Sun before beginning its eternal journey toward interstellar space. Only required systematic astrometric observations over several months to establish the object's orbital parameters with sufficient precision to confirm its hyperbolic trajectory and calculate its past and future positions with mathematical certainty. Only needed precise mathematical analysis to demonstrate that 3E Atlas carries sufficient velocity to escape solar gravitational influence and continue traveling between stellar systems. Trajectory analysis techniques employ sophisticated mathematical methods, including numerical integration of gravitational perturbations from all major planets, relativistic corrections for close solar approach, and radiation pressure effects that might modify apparent orbital parameters through systematic forces beyond simple gravitational attraction. These analysis methods require supercomputer calculations that account for multiple gravitational influences while determining precise orbital elements that characterize the object's motion through three-dimensional space and time. The mystery of approach velocity involves understanding how 3I Atlas acquired the enormous kinetic energy necessary to achieve interstellar travel velocities that exceed 30 kilometers per second relative to the local stellar neighborhood, suggesting complex gravitational interactions with massive stellar objects or participation in high-energy astrophysical processes that accelerated the object to speeds enabling interstellar migration. Current models suggest gravitational slingshot effects from close encounters with giant planets or stellar systems may provide acceleration mechanisms. Perihelion passage calculations determine that 3I Atlas reached its closest approach to the Sun in late 2019, achieving minimum solar distance while experiencing maximum gravitational acceleration and thermal heating that provided optimal conditions for spectroscopic analysis and physical characterization through enhanced brightness and observational accessibility. This perihelion timing determined the observational window available for detailed study, while establishing optimal observation scheduling for maximum scientific return. Escape velocity analysis demonstrates that 3I Atlas carries more than sufficient kinetic energy to escape not only solar gravitational influence, but also the gravitational binding of the local stellar neighborhood, indicating that the object will continue traveling through interstellar space indefinitely unless captured by gravitational interaction with other stellar systems encountered during its galactic journey. These velocity calculations provide insights into the object's ultimate fate and potential for future stellar system encounters. Asymptotic velocity measurements indicate that 3I Atlas will eventually achieve a final velocity of approximately 40 km per second, relative to the Sun as it escapes to infinite distance, representing the object's intrinsic velocity through interstellar space before gravitational modification by solar system passage. This asymptotic velocity provides clues about the object's origin and the stellar environment from which it was ejected or accelerated toward our solar system. Galactic motion corrections account for the Sun's orbital motion around the galactic center and local stellar motions that affect apparent interstellar object velocities and trajectory directions when analyzed from solar system reference frames. These corrections enable determination of 3I Atlas motion relative to the local standard of rest, and provide insights into galactic dynamics and stellar kinematics that affect interstellar object populations and their apparent characteristics. Relativistic effects become significant for objects like 3I Atlas during close solar approach, where high velocities and strong gravitational fields require corrections to Newtonian mechanics through general relativistic calculations that account for space-time curvature and relativistic mass-energy relationships. These relativistic corrections ensure accurate trajectory predictions while demonstrating extreme physical conditions encountered during hyperbolic solar system passage. Radiation pressure effects supplement gravitational forces through systematic momentum transfer from solar photons that can measurably affect trajectories of small objects like 3I Atlas, particularly during close solar approach, when intense solar radiation creates systematic forces that modify orbital parameters and must be accounted for in precision trajectory calculations. These radiation effects provide information about object size and surface properties, while demonstrating non-gravitational forces affecting interstellar object motion. Planetary perturbations create systematic modifications to hyperbolic trajectories as 3I Atlas passes through the solar system and experiences gravitational influences from Jupiter, Saturn, and other massive planets that slightly alter its path while providing additional constraints on trajectory analysis and orbital determination accuracy. These perturbations require precise calculation while offering opportunities to refine orbital parameters through systematic analysis of gravitational interactions. Future trajectory predictions enable calculation of 3I Atlas position and velocity at any future time, while determining its eventual path through local stellar neighborhoods and potential encounters with nearby stellar systems during its continued interstellar journey. These predictions demonstrate the object's ultimate fate, while providing opportunities for future observational campaigns if improved telescopes enable detection at greater distances. Historical trajectory reconstruction allows calculation of 3I Atlas past motion through interstellar space and identification of its probable origin direction relative to local stellar populations and nearby stellar systems that might have provided gravitational acceleration or served as the object's formation location millions of years ago. These reconstructions provide insights into galactic dynamics and interstellar object transport mechanisms. Observational validation of hyperbolic trajectories requires systematic comparison between predicted and observed positions to verify mathematical models and demonstrate the accuracy of orbital determination methods, while confirming that observed motion matches theoretical expectations for objects following hyperbolic paths through solar gravitational fields. These validations ensure scientific rigor while building confidence in interstellar object identification methods. Modern computational methods enable precise calculation of hyperbolic trajectories through advanced numerical integration techniques and sophisticated mathematical algorithms that account for multiple gravitational influences while providing accurate predictions of object motion throughout solar system passage and beyond. Contemporary computational capabilities continue improving trajectory analysis, precision, while enabling more detailed study of interstellar object dynamics. Tonight, every mathematical curve that describes planetary motion, every gravitational calculation that predicts celestial mechanics, every demonstration of how mathematical analysis reveals cosmic origins carries forward the legacy of 3i Atlas and the systematic application of mathematical physics to astronomical discovery that transforms observed positions into comprehensive understanding of cosmic visitors and their journeys through interstellar space. Too fast, too strange for local origin becomes evident when detailed velocity analysis of 3i Atlas reveals approach speeds that exceed the solar system's escape velocity by substantial margins, demonstrating kinetic energy levels that could only result from gravitational acceleration by stellar systems located far beyond our Sun's gravitational influence. The object's velocity measurements indicate that it entered the solar system carrying approximately 42 kilometers per second of excess velocity relative to the Sun's local rest frame, representing kinetic energy that no internal solar system process could have provided to an object that formed within our stellar neighborhood during the past 4.6 billion years of solar system evolution. Solar system escape velocity calculations establish the minimum speed required for any object to permanently escape solar gravitational influence, which varies with distance from the Sun but approaches approximately 42 kilometers per second at Earth's orbital distance when measured relative to the Sun's center of mass. Objects achieving velocities significantly exceeding these escape thresholds carry clear evidence of external energy sources, as solar system gravitational dynamics cannot accelerate native objects beyond escape velocity without additional energy input from sources outside the local gravitational system. Velocity distribution analysis among known solar system objects demonstrates systematic patterns where planets, asteroids, and comets exhibit orbital velocities that remain well below escape thresholds, with maximum velocities typically occurring during close solar approaches that temporarily increase orbital speeds while maintaining bound elliptical trajectories. The velocity characteristics of 3i Atlas exceed these normal solar system velocity ranges by factors of 2 to 3, placing the object in a kinematic category that requires explanation through external acceleration mechanisms. Only took 3i Atlas approximately 1 million years to travel from the nearest stellar systems to our solar system, while maintaining velocities that indicate systematic acceleration by gravitational interaction with massive stellar objects or participation in high-energy astrophysical processes that provided the enormous kinetic energy necessary for interstellar travel. Only required gravitational analysis to demonstrate that such velocities exceed any acceleration mechanism available within the solar system's current gravitational environment. Only needed comparative analysis with solar system object velocities to establish that 3i Atlas carries clear kinematic signatures of external origin. Gravitational acceleration mechanisms that could produce 3i Atlas velocities include close encounters with massive stellar objects, gravitational slingshot effects during planetary system formation or evolution, stellar collision events, or ejection from binary stellar systems through three-body gravitational interactions that transfer orbital energy into translational kinetic energy. These acceleration scenarios require extreme gravitational environments that exceed typical solar system conditions, while providing energy sources capable of accelerating objects to interstellar travel velocities. The mystery of velocity acquisition involves understanding the specific astrophysical processes that provided 3i Atlas with sufficient kinetic energy to escape its formation location and achieve interstellar travel capabilities. As most theoretical models suggest that typical planetary system processes rarely generate velocities exceeding local escape speeds by the substantial margins observed in confirmed interstellar objects, current hypotheses require exotic formation scenarios or unusual gravitational environments that remain uncommon in typical stellar system evolution. Kinetic energy calculations for 3I Atlas reveal total energy content that depends on the object's mass, but likely represents energy equivalent to major astronomical events such as planetary collisions, stellar close encounters, or gravitational interactions involving massive objects like brown dwarfs or stellar companions. These energy estimates provide constraints on formation mechanisms while indicating the extreme astrophysical processes necessary to accelerate objects to observed interstellar velocities. Stellar encounter modeling suggests that 3I Atlas may have experienced gravitational interaction with massive stellar objects during its formation or ejection from its origin system. Where close approaches to stars, brown dwarfs, or massive planets could provide sufficient gravitational acceleration to achieve interstellar escape velocities through systematic energy transfer during gravitational slingshot encounters. These encounter models require specific geometric and timing conditions that occur rarely in typical stellar environments. Galactic velocity context places 3I Atlas motion within the framework of local stellar kinematics and galactic rotation patterns that affect apparent velocities when measured from solar system reference frames. The object's velocity relative to local stellar populations indicates motion that significantly exceeds typical stellar velocities in the local galactic neighborhood, suggesting either acceleration by unusual astrophysical processes or origin in stellar environments with different kinematic characteristics than local stellar populations. Binary system ejection mechanisms provide plausible explanations for 3I Atlas velocities through gravitational interactions in binary or multiple stellar systems where gravitational instabilities can eject planets, asteroids, or cometary materials at velocities exceeding local escape speeds. These ejection processes operate through three-body gravitational dynamics that can transfer orbital energy into translational motion while accelerating objects to interstellar travel velocities through systematic gravitational interactions. Planetary formation violence during early stellar system evolution may generate 3 Atlas-type objects through catastrophic collisions, gravitational scattering, or dynamical instabilities that eject planetary materials at high velocities during chaotic phases of planetary system assembly. These violent formation processes could accelerate debris to interstellar velocities while creating populations of high-velocity objects that migrate between stellar systems through galactic space. Hyperbolic excess velocity measurements quantify the amount by which 3I Atlas velocity exceeds solar escape velocity, providing systematic measures of the external energy input required to achieve observed kinematic characteristics. These excess velocity measurements enable comparison with theoretical acceleration mechanisms while constraining models of interstellar object formation and acceleration processes in alien stellar environments. Trajectory reconstruction calculations enable determination of 3I Atlas motion through interstellar space before solar system encounter, providing insights into its origin direction and probable stellar system interactions during its million-year journey between stars. These reconstructions suggest approach from the direction of the Vega stellar system, though gravitational perturbations during interstellar travel complicate precise origin determination and require statistical analysis of probable source regions. Acceleration history analysis attempts to identify systematic velocity changes during 3I Atlas passage through the solar system that might indicate non-gravitational forces such as outgassing, radiation pressure, or other mechanisms that could modify apparent velocities and affect trajectory analysis. These acceleration studies provide insights into object composition and surface properties while testing theoretical models of interstellar object behavior during solar system passage. Comparative velocity analysis with other interstellar objects like Oumuamua and Tuai-Borisov reveals systematic patterns in interstellar object velocities that provide insights into formation mechanisms and galactic populations of high-velocity objects migrating between stellar systems. These comparative studies suggest that interstellar objects exhibit velocity distributions that reflect specific acceleration mechanisms while indicating common processes that create interstellar traveling populations. Statistical implications of 3I Atlas velocities contribute to understanding the frequency and characteristics of interstellar object populations, while providing constraints on theoretical models of galactic material exchange and stellar system evolution. The object's kinematic properties suggest that high-velocity interstellar travelers represent a significant population that remains largely undetected due to observational limitations and brief solar system passage times. Modern astrometry techniques enable precise velocity measurements for objects like 3I Atlas through sophisticated observational methods and mathematical analysis that provide accurate kinematic characterization despite observational challenges imposed by small size, great distance, and rapid motion through solar system space. Contemporary measurement capabilities continue improving velocity determination precision while enabling better understanding of interstellar object kinematics. Tonight, every measurement of cosmic velocity, every calculation that reveals gravitational acceleration, every demonstration of how kinematic analysis distinguishes local from external origins carries forward the legacy of 3I Atlas and the systematic application of celestial mechanics to astronomical discovery that reveals the violent astrophysical processes operating in distant stellar systems through direct examination of high-velocity cosmic refugees that carry kinematic signatures of their exotic formation environments. Brightness variations that defied logic emerge as 3I Atlas exhibits irregular fluctuations in reflected light that don't conform to typical rotation patterns expected from asteroids or the systematic brightening anticipated from comets approaching the Sun, creating observational puzzles that challenge fundamental assumptions about how small celestial objects behave when illuminated by solar radiation. These brightness changes operate on timescales ranging from hours to days, while displaying amplitude variations that suggest either complex three-dimensional geometry, heterogeneous surface composition, or unusual rotation dynamics that differ systematically from normal solar system object behavior patterns. Photometric analysis techniques measure systematic brightness changes in 3I Atlas through precise monitoring of reflected sunlight intensity over extended observation periods, where digital detectors record subtle variations in luminosity that reveal information about object rotation, surface properties, and geometric characteristics. These measurements require careful correction for atmospheric effects, telescope instrumental variations, and changing observational geometry as both Earth and the target object move along their respective orbital paths during the observation campaign. Rotation period. Determination becomes complicated when 3I Atlas brightness variations fail to exhibit the regular periodicity expected from objects undergoing simple rotation about fixed axes, instead showing complex variation patterns that suggest either tumbling motion, multiple rotation periods, or systematic changes in surface reflectivity that operate independently of rotational geometry. Traditional asteroid rotation analysis relies on periodic brightness changes that reflect different surface areas becoming visible as objects spin. But 3i Atlas variations don't conform to these standard patterns. Only took astronomical observations approximately weeks to establish that 3i Atlas brightness behavior differed significantly from typical asteroid and comet photometric patterns through systematic monitoring that revealed irregular variation amplitudes and timescales that challenge conventional interpretation methods. Only required comparative analysis with known solar system objects to demonstrate that the observed brightness changes represent unusual behavior that requires explanation through exotic physical properties or unconventional geometric characteristics. Only needed extended photometric monitoring to document systematic deviations from expected brightness patterns. Light curve analysis reveals systematic patterns in 3 Atlas brightness variations that provide insights into possible shape characteristics, surface composition variations, and rotation dynamics despite the complexity and irregularity of observed photometric behavior. These light curves create systematic databases of brightness measurements that enable statistical analysis and theoretical modeling, while providing observational constraints on physical property hypotheses and geometric models that attempt to explain unusual photometric characteristics. The mystery of brightness interpretation involves understanding whether 3i Atlas photometric variations result from geometric effects related to irregular shape and complex rotation, surface composition heterogeneity that creates systematic reflectivity differences across the object's surface, or exotic physical processes that operate differently than normal solar system object behavior. The unusual brightness patterns require explanation through theoretical models that account for interstellar object formation and evolution under conditions that may differ from solar system environment. Surface composition effects on brightness variations could result from systematic differences in mineral composition, thermal properties, or chemical processing during interstellar travel that create heterogeneous surface characteristics affecting reflected light intensity in ways that depend on illumination geometry and observational viewing angles. These composition effects would create systematic brightness variations that reflect surface diversity while providing information about formation conditions and space weathering processes during interstellar migration. Geometric modeling attempts to reproduce 3 Atlas brightness variations through three-dimensional shape models and rotation dynamics that could generate observed photometric patterns despite irregular variation characteristics that challenge conventional analysis methods. These models require sophisticated mathematical analysis and computer simulations that test various shape hypotheses while attempting to match theoretical predictions with observed brightness measurements under different illumination and viewing geometries. Thermal effects on brightness may contribute to 3i Atlas. Photometric variations through systematic temperature changes that affect surface material properties and thermal emission characteristics as the object approaches and recedes from the Sun during its hyperbolic passage through the inner solar system. These thermal effects supplement reflected light measurements while potentially creating brightness variations that operate independently of geometric factors through temperature-dependent surface property changes. Outgassing signatures in brightness measurements could indicate minimal cometary activity that affects surface reflectivity through dust production or surface modification without creating obvious comet-like tails or comas visible in telescopic observations. These subtle outgassing effects might create systematic brightness variations that reflect ongoing surface processes while providing insights into internal composition and volatile content despite the object's generally inactive appearance. Observational challenges in brightness measurement arise from 3-eye atlas small apparent size, rapid motion across the sky, and changing distance from both Earth and Sun that create systematic measurement difficulties requiring sophisticated observational techniques and careful data reduction procedures. These challenges affect photometric precision while limiting the quality and quantity of brightness measurements available for analysis and theoretical modeling of physical properties. Instrumental effects on brightness measurements include systematic variations in telescope response, atmospheric transparency changes, and detector calibration uncertainties that must be carefully corrected to isolate genuine object brightness variations from observational artifacts that could mimic physical processes or geometric effects. These instrumental considerations require rigorous observational protocols and data reduction procedures that ensure measurement reliability while enabling confident interpretation of photometric results. Statistical analysis of brightness variations employs mathematical techniques that identify systematic patterns, periodic components, and correlation relationships within complex photometric datasets that may reveal underlying physical processes despite irregular variation characteristics that complicate traditional analysis methods. These statistical approaches provide systematic frameworks for extracting information from complex brightness measurements while testing theoretical models against observational constraints. Comparative photometry with other interstellar objects enables systematic analysis of brightness behavior patterns among confirmed visitors from beyond the solar system, while identifying common characteristics and unique features that provide insights into interstellar object populations and formation mechanisms. These comparative studies reveal whether 3-eye atlas brightness behavior represents typical interstellar object characteristics or unusual features that require specific formation or evolution scenarios. Theoretical modeling of brightness variations requires sophisticated physical models that account for possible shape distributions, surface composition variations, rotation dynamics, and thermal effects that could produce observed photometric patterns while remaining consistent with interstellar object formation and evolution theories. These theoretical frameworks provide systematic approaches for interpreting brightness measurements while testing hypotheses about physical properties and formation mechanisms. Polarimetric analysis supplements brightness measurements through systematic study of reflected light polarization characteristics that provide additional information about surface properties, particle sizes, and composition, while offering independent constraints on theoretical models that attempt to explain unusual brightness behavior. These polarimetric observations provide complementary datasets that enhance understanding of surface characteristics and physical properties. Future brightness monitoring opportunities may arise if improved telescopes enable continued observation of 3 atlas at greater distances, while the object continues its journey away from the solar system, providing extended baseline measurements that could reveal long-term brightness variations and enable better understanding of systematic photometric behavior patterns. These future observations would enhance scientific understanding while providing additional constraints on theoretical models. Modern photometric techniques enable precise brightness measurements for small, distant objects like 3-eye atlas through advanced detector technology, sophisticated data reduction methods, and systematic observational protocols that maximize measurement precision while minimizing systematic errors and observational biases. Contemporary photometric capabilities continue improving measurement quality while enabling better characterization of unusual objects and exotic phenomena. Tonight, every systematic measurement of celestial brightness, every careful analysis that reveals object properties through reflected light, Every demonstration of how photometric observations provide insights into distant object characteristics carries forward the legacy of Three-Eye Atlas and the systematic application of observational astronomy to cosmic mystery solving that transforms subtle brightness variations into comprehensive understanding of exotic objects visiting from interstellar space. The composition mystery deepens as spectroscopic analysis of Three-Eye Atlas reveals chemical signatures that don't clearly match known asteroid or comet compositions from our solar system, suggesting either exotic materials formed under different stellar conditions or chemical processing during millions of years of interstellar travel that modified original surface properties in ways that create spectral characteristics unlike any terrestrial or solar system materials. These compositional uncertainties reflect fundamental limitations in remote sensing capabilities when applied to small, distant objects whose surface chemistry may have developed under astrophysical conditions that differ systematically from solar system formation environments. Spectroscopic observation techniques measure reflected and emitted light from Three-Eye Atlas across multiple wavelength ranges to identify characteristic absorption and emission features that correspond to specific minerals, molecules, and chemical compounds present on the object's surface. These spectroscopic measurements require sophisticated instruments and careful data reduction procedures that separate genuine surface composition signals from atmospheric interference, instrumental artifacts, and observational noise that can obscure subtle spectral features indicating material properties and chemical composition. Chemical signature interpretation involves comparing Three-Eye Atlas spectral characteristics with laboratory measurements of known materials and theoretical models of mineral optical properties to identify possible surface compositions and constrain formation mechanisms that could produce observed spectral features. This comparative analysis requires extensive databases of material optical properties and sophisticated modeling techniques that account for observational geometry, thermal effects, and space weathering processes that modify surface spectral characteristics. Only took spectroscopic observations approximately months to establish that Three-Eye Atlas exhibits spectral characteristics that differ systematically from typical asteroid and comet populations through systematic analysis that revealed absorption features and reflectance properties that don't match standard meteorite and solar system object classifications. Only required comparative spectroscopic analysis to demonstrate that the object's surface composition represents either unusual material properties or chemical processing that creates distinctive spectral signatures, requiring explanation through exotic formation or evolution mechanisms. Only needed systematic spectral measurement to document compositional characteristics that challenge conventional solar system material classification systems. Mineral identification challenges arise when Three-Eye Atlas spectral features remain too weak, broad, or ambiguous to enable definitive identification of specific mineral compositions through standard spectroscopic analysis techniques that rely on sharp, well-defined absorption features corresponding to known mineral optical properties. These identification difficulties reflect both observational limitations imposed by object size and distance, and possible surface properties that don't conform to standard mineral compositions found in solar system materials. The mystery of exotic composition involves understanding whether Three Atlas surface materials represent genuinely unusual chemical compositions that formed under different stellar conditions, or whether standard solar system materials have been chemically modified through interstellar space, weathering processes that alter optical properties and create spectral characteristics that differ from laboratory measurements of unprocessed materials. Current scientific understanding provides limited constraints on interstellar space, weathering effects, and exotic material formation mechanisms. Space weathering effects during interstellar travel may systematically alter 3I Atlas surface composition through cosmic ray bombardment, micrometeorite impacts, and chemical reactions with interstellar medium materials that modify original surface properties while creating new chemical compounds and optical characteristics that differ from unprocessed materials. These space weathering processes operate over million-year timescales, while potentially creating surface modifications that obscure original compositional signatures. Formation environment differences between stellar systems could produce 3I Atlas compositional characteristics through planetary formation processes that operate under different chemical conditions, temperature regimes, or elemental abundance patterns that create mineral assemblages and chemical compositions, unlike those found in solar system materials formed under local stellar conditions. These formation differences would create systematic compositional variations that reflect different stellar neighborhood chemistry and planetary system evolution. Thermal processing during solar approach creates systematic heating effects that may modify 3I Atlas surface composition through mineral phase transitions, volatile loss, or chemical reactions that alter optical properties and spectral characteristics, while the object experiences elevated temperatures during perihelion passage. These thermal effects supplement observational challenges while potentially creating compositional changes that complicate interpretation of spectral measurements and material identification. Instrumental limitations in spectroscopic analysis include systematic constraints on spectral resolution, wavelength coverage, and signal-to-noise ratios that affect the quality and interpretability of compositional measurements for small, faint objects like 3I Atlas. These limitations require careful consideration when interpreting spectroscopic results, while highlighting technological challenges that affect remote sensing capabilities for interstellar objects and other exotic astronomical targets. Comparative analysis with meteorite samples provides systematic frameworks for interpreting 3I Atlas compositional measurements through comparison with known solar system materials that represent various formation environments and chemical processing histories within our local stellar neighborhood. These comparative studies reveal whether interstellar object compositions fall within known solar system material ranges or represent genuinely exotic compositions requiring explanation through formation under different stellar conditions. Laboratory analog studies create controlled experimental conditions that simulate possible 3I Atlas formation environments and space weathering processes to understand how different chemical and physical conditions might produce observed spectral characteristics through systematic material processing and surface modification. These laboratory studies provide theoretical frameworks for interpreting compositional measurements, while testing hypotheses about formation mechanisms and evolution processes. Infrared spectroscopy techniques enable detection of molecular vibration features and thermal emission characteristics that provide additional constraints on 3I Atlas surface composition through wavelength ranges that reveal different chemical information than visible light spectroscopy. These infrared measurements supplement visible spectroscopic observations while providing independent evidence about material properties and chemical composition through different observational techniques. Contamination effects from solar system materials could potentially modify 3I Atlas apparent composition through accretion of interplanetary dust, solar wind particles, or other solar system materials during passage through the inner solar system, creating apparent compositional characteristics that don't reflect original interstellar object properties. These contamination possibilities require careful consideration when interpreting compositional measurements and comparing with theoretical formation models. Statistical uncertainty analysis in compositional measurements accounts for observational noise, systematic measurement errors, and model-dependent interpretation uncertainties that affect confidence levels in material identification and chemical composition determination. These uncertainty analyses provide systematic frameworks for evaluating compositional hypotheses while establishing reliability limits for spectroscopic interpretation and theoretical modeling applications. Theoretical composition modeling attempts to predict 3I atlas surface materials through models of planetary formation processes under different stellar conditions, interstellar space weathering effects, and chemical evolution during million-year journeys between stellar systems. These theoretical frameworks provide systematic approaches for interpreting compositional measurements while testing formation hypotheses and evolution scenarios against observational constraints. Multi-wavelength observations combine spectroscopic measurements across visible, infrared, and other wavelength ranges to provide comprehensive characterization of 3I atlas, surface properties and chemical composition through complementary observational techniques that reveal different aspects of material properties and formation history. These multi-wavelength approaches maximize information extraction while providing systematic validation of compositional interpretation and theoretical modeling. Future compositional analysis opportunities may arise through improved spectroscopic techniques, space-based observations that eliminate atmospheric interference, or potential sample return missions that could provide direct laboratory analysis of interstellar object materials. These future capabilities would revolutionize compositional understanding while providing definitive constraints on formation mechanisms and chemical evolution processes. Modern spectroscopic capabilities enable sophisticated compositional analysis of small astronomical objects through advanced instrumentation, improved detector technology, and systematic observational techniques that maximize scientific information extraction despite challenging observational conditions imposed by object size, distance, and motion. Contemporary spectroscopic methods continue advancing analytical capabilities while enabling better understanding of exotic object compositions. Tonight, every spectroscopic measurement that reveals material composition, every laboratory analysis that identifies chemical signatures, every systematic comparison that distinguishes exotic from familiar materials carries forward the legacy of 3I atlas and the ongoing quest to understand cosmic chemistry through remote sensing techniques that transform reflected light into comprehensive knowledge about materials formed in distant stellar environments. Size estimates that keep changing reflect the fundamental observational challenges astronomers face when attempting to determine the actual dimensions of 3I atlas. As scientists struggle with uncertain reflectivity properties and irregular shape characteristics that create systematic ambiguities in size determination, with estimates varying by orders of magnitude depending on assumptions about surface brightness and geometric properties. This size albedo degeneracy represents one of the most persistent problems in asteroid and interstellar object characterization, where identical apparent brightness can result from either small, highly reflective objects or larger, dark objects, creating measurement uncertainties that profoundly affect understanding of physical properties and formation mechanisms. Albedo-size relationship governs the fundamental physics of brightness measurements, where apparent magnitude depends on both object cross-sectional area and surface reflectivity, according to mathematical relationships that create systematic degeneracies when only brightness information is available for analysis. An object with 10% surface reflectivity appears identical to one with 1% reflectivity if the darker object has 10 times the cross-sectional area. creating ambiguities that require additional observational constraints or theoretical assumptions to resolve size determination uncertainties. Brightness measurement limitations for 3i atlas arise from the object's small apparent size, great distance from Earth, and rapid motion through the solar system that create observational challenges requiring sophisticated telescopes and careful measurement techniques to achieve sufficient photometric precision for reliable size analysis. These observational constraints affect measurement quality while limiting the accuracy of size estimates derived from brightness analysis and theoretical modeling applications. Only took astronomical observations approximately weeks to reveal systematic uncertainties in 3i atlas size determination through brightness measurements that could be consistent with objects ranging from tens of meters to several kilometers in diameter, depending on assumptions about surface reflectivity and geometric properties. Only required comparative analysis with known solar system objects to demonstrate that size uncertainty represents a fundamental limitation in remote sensing techniques when applied to small, distant objects with unknown surface properties. Only needed systematic photometric analysis to establish that size estimates remain highly model dependent and require additional observational constraints for reliable determination. Thermal infrared observations provide the most reliable method for breaking size albedo degeneracies through measurement of thermal emission that depends primarily on object size and temperature, while remaining relatively independent of surface reflectivity, characteristics that affect visible light observations. These thermal measurements enable determination of both size and albedo through combined analysis of reflected and emitted radiation, but require sensitive infrared telescopes and favorable observational geometry that may not be available for rapidly moving interstellar objects. The mystery of shape complexity compounds size determination challenges when 3i atlas exhibits irregular geometry that creates systematic variations in apparent cross-sectional area depending on viewing angle and rotation orientation, making simple spherical size estimates inappropriate while requiring three-dimensional shape modeling that accounts for complex geometric effects on brightness and thermal emission measurements. Current observational limitations prevent detailed shape determination while creating additional uncertainties in size analysis. Radar observation attempts could potentially provide direct size measurements through reflected radio waves that determine object dimensions independent of surface optical properties. But 3i atlas' small size, great distance, and rapid motion create technical challenges that exceed current radar astronomy capabilities for detecting and characterizing small interstellar objects during their brief passages through the inner solar system. These radar limitations highlight technological constraints that affect direct size measurement opportunities. Statistical size estimation employs probabilistic analysis of 3i atlas, brightness measurements combined with assumed distributions of surface reflectivity properties derived from solar system object populations to provide statistical estimates of probable size ranges despite fundamental measurement ambiguities. These statistical approaches acknowledge uncertainty while providing systematic frameworks for size analysis that account for observational limitations and theoretical constraints on material properties. Comparative sizing analysis uses 3i atlas brightness characteristics compared with similar solar system objects of known size and albedo to infer probable dimensions through analogy with objects exhibiting similar photometric properties and spectral characteristics. These comparative approaches assume that interstellar objects share material properties with solar system analogues, while providing size estimates that depend on the validity of compositional and surface property assumptions. Geometric modeling attempts to constrain 3i atlas size through analysis of brightness variation patterns that may reveal information about object shape and rotation characteristics, despite irregular photometric behavior that complicates traditional analysis methods. These geometric approaches require sophisticated mathematical modeling while providing size constraints that depend on assumptions about rotation dynamics and surface property uniformity. Resolution limitations of current telescopes prevent direct imaging of 3i atlas surface features or overall shape characteristics that could provide independent size constraints through geometric analysis of resolved surface details or limb measurements. These resolution constraints highlight technological limitations while emphasizing dependence on indirect measurement techniques that require theoretical assumptions for size determination. Parallax measurements could theoretically provide independent distance verification that would improve size estimates through precise determination of 3i atlas distance from Earth during observational campaigns. But the object's rapid motion and small parallax signatures create measurement challenges that exceed current astrometric precision capabilities for moving targets. These parallax limitations affect geometric analysis while highlighting observational constraints on direct distance measurement. Systematic uncertainty analysis accounts for various sources of measurement error and theoretical assumption limitations that affect size, determination, reliability, while providing statistical frameworks for evaluating confidence levels in size, estimates, and identifying dominant uncertainty sources that limit measurement precision. These uncertainty analyses provide systematic approaches for evaluating size determination reliability, while guiding observational strategy development and theoretical modeling applications. Model-dependent estimates reflect the systematic dependence of size determination on theoretical assumptions about surface properties, geometric characteristics, and thermal behavior that may not accurately represent 3i atlas actual physical properties, creating systematic biases that affect size estimate reliability while highlighting fundamental limitations in remote sensing techniques applied to exotic objects with unknown characteristics. Technological limitations in size determination emphasize current constraints in astronomical instrumentation and observational techniques that prevent definitive size measurement for small, distant objects like 3i atlas, while highlighting opportunities for improved measurement capabilities through advanced telescope technology and novel observational approaches. These limitations affect scientific understanding while motivating technological development for better interstellar object characterization. Future size determination opportunities may arise through improved infrared observational capabilities, space-based telescopes that eliminate atmospheric limitations, or potential close-approach missions that could provide direct size measurements through high-resolution imaging or radar techniques. These future capabilities would revolutionize size determination accuracy while providing definitive constraints on interstellar object physical properties and formation mechanisms. Calibration challenges in size determination require systematic validation of measurement techniques and theoretical models through comparison with objects of known size and properties, while identifying systematic biases and measurement uncertainties that affect size estimate reliability. These calibration procedures provide quality control frameworks while ensuring measurement accuracy and theoretical model validation for size determination applications. Modern observational techniques continue improving size determination capabilities through advanced photometric methods, sophisticated data analysis techniques, and systematic observational strategies that maximize information extraction from brightness measurements, despite fundamental limitations imposed by size albedo degeneracies and observational constraints. Contemporary measurement capabilities provide systematic approaches for size analysis while acknowledging inherent limitations and uncertainty sources. Tonight, every careful measurement of cosmic brightness, every systematic analysis that attempts to distinguish size from surface properties, every demonstration of observational limitations in remote sensing carries forward the legacy of 3i Atlas and the ongoing challenge of determining fundamental physical properties of distant objects through indirect measurement techniques that require sophisticated analysis and careful consideration of systematic uncertainties. The missing comet tail puzzle emerges as one of the most perplexing aspects of 3i Atlas behavior, where despite approaching within a quarter astronomical unit of the Sun, and experiencing intense solar heating that should vaporize surface ices and create spectacular comet-like tails. The object shows minimal signs of typical comet outgassing or tail formation that characterizes most icy bodies during close solar encounters. This absence of obvious cometary activity challenges fundamental assumptions about interstellar object composition, while suggesting either unusual surface properties, exotic ice compositions, or depletion mechanisms that prevent normal comet behavior, despite solar heating that should activate volatile sublimation, comet tail formation. Physics operates through systematic sublimation of water ice, carbon dioxide, and other volatile compounds when solar heating raises surface temperatures above sublimation thresholds, creating gas and dust emission that forms characteristic coma and tails through radiation pressure and solar wind interaction. These tail formation processes represent well-understood physical mechanisms that operate predictably for solar system comets, making the absence of obvious tail formation in 3i Atlas a significant observational puzzle that requires explanation through exotic composition or unusual surface properties. Solar heating calculations for 3i Atlas perihelion passage indicate surface temperatures that should reach several hundred Kelvin, well above sublimation temperatures for water ice, carbon dioxide, and most other volatile compounds typically found in cometary nuclei. These thermal calculations suggest that any surface ices should undergo vigorous sublimation during solar approach, creating gas production rates sufficient to generate observable cometary activity if 3i Atlas contains typical cometary volatile inventories and surface characteristics. Only took 3i Atlas approximately months of solar approach to reach thermal conditions that should activate vigorous outgassing in normal cometary materials through solar heating that exceeds sublimation thresholds for most volatile compounds found in solar system comets. Only required systematic observational monitoring to establish that the object exhibits minimal cometary activity, despite thermal conditions that should produce obvious gas and dust emission if the object contained typical cometary ice compositions. Only needed comparative analysis with known comets at similar solar distances to demonstrate that 3i Atlas behavior represents unusual inactivity that requires explanation through exotic properties. Volatile depletion mechanisms could explain 3i Atlas' lack of cometary activity through systematic loss of surface ices during millions of years of interstellar travel, where cosmic ray heating, stellar radiation, and sublimation in the vacuum of space gradually remove volatile compounds and leave behind refractory materials that resist outgassing during solar heating. These depletion processes would create objects that appear inactive, despite potential internal ice content that remains inaccessible beneath processed surface layers. The mystery of surface composition involves understanding whether 3i Atlas represents a fundamentally different type of object that lacks volatile compounds entirely, or whether typical cometary materials remain present but inaccessible due to surface processing. Unusual ice compositions, or exotic thermal properties that prevent normal outgassing behavior. Current observational limitations prevent definitive determination of internal composition, while leaving fundamental questions about object nature and formation mechanisms unresolved. Mantle formation processes during interstellar travel may create protective surface layers that prevent volatile sublimation by forming thermal insulation barriers composed of refractory dust and organic compounds that resist solar heating while protecting internal ices from thermal activation. These mantle effects operate through systematic surface processing that creates protective coatings while potentially preserving internal volatile content despite apparent surface inactivity. Sublimation threshold effects may prevent 3I Atlas outgassing if the object's volatile compounds exist in chemical forms or physical states that require higher activation energies than typical cometry ices, creating systematic differences in sublimation behavior that prevent obvious gas production, despite solar heating that activates normal cometry materials. These threshold effects could result from exotic ice compositions or chemical processing during interstellar travel. Observational sensitivity limitations may prevent detection of minimal outgassing activity from 3I Atlas if gas and dust production rates remain below current observational thresholds, while still representing active cometry processes that operate at reduced intensities compared to typical solar system comets. These sensitivity constraints could mask subtle cometry activity, while creating apparent inactivity that doesn't reflect actual physical processes. Dust production analysis attempts to identify minimal particle emission from 3I Atlas through sensitive photometric monitoring and coma detection techniques that search for systematic brightness enhancements or asymmetric features that might indicate ongoing dust production despite the absence of obvious cometry tails. These dust studies provide systematic approaches for detecting minimal activity while testing theoretical models of reduced outgassing intensity. Gas emission spectroscopy employs sensitive spectroscopic techniques to search for characteristic emission lines from common cometry gas species, including water vapor, carbon monoxide, carbon dioxide, and other volatile compounds that might indicate ongoing sublimation activity despite the absence of visible comae or tails. These spectroscopic observations provide direct chemical evidence for outgassing, while testing hypotheses about reduced activity levels and exotic composition. Thermal modeling of 3I Atlas internal structure attempts to predict subsurface temperature distributions and volatile sublimation patterns that could explain observed activity levels through theoretical analysis of heat conduction, sublimation physics, and gas transport within assumed internal compositions and structural configurations. These thermal models provide systematic frameworks for interpreting observational constraints while testing hypotheses about internal properties and composition. Comparative analysis with other interstellar objects reveals systematic patterns in cometry activity levels among confirmed visitors from beyond the solar system, where objects like TUI Borisov exhibit obvious cometry behavior, while others like Oumuamua and 3I Atlas show minimal obvious activity despite solar heating. These comparative studies suggest diversity in interstellar object composition while providing insights into formation mechanisms and evolution processes. Space weathering effects on volatile content may systematically alter 3I Atlas surface and subsurface volatile inventories through cosmic ray processing, micrometeorite bombardment, and chemical reactions during interstellar travel that modify original cometry compositions while creating objects that exhibit reduced activity despite potential internal volatile content. These space weathering processes operate over million-year timescales while potentially explaining apparent compositional differences. Surface structure effects could influence 3I Atlas outgassing behavior through surface roughness, porosity, or layering characteristics that affect heat conduction and gas transport, while creating systematic differences in sublimation efficiency compared to typical cometry surface properties. These structural effects might prevent efficient gas production while maintaining internal volatile content that remains thermally inaccessible during solar heating. Detection threshold calculations provide systematic analysis of minimum gas and dust production rates that could be detected with current observational capabilities, while establishing lower limits on 3I Atlas activity levels that constrain theoretical models of composition and outgassing processes. These threshold analyses provide quantitative frameworks for evaluating activity constraints, while guiding theoretical interpretation of observational limitations. Future observational opportunities for detecting 3I Atlas cometry activity may arise through improved instrumental sensitivity, space-based observations that eliminate atmospheric interference, or extended monitoring programs that could detect delayed or variable outgassing activity that operates on different timescales than typical cometry behavior. These future capabilities would enhance understanding while providing better constraints on composition and activity mechanisms. Modern cometry observation techniques enable sensitive detection of minimal outgassing activity through advanced spectroscopic methods, sophisticated photometric analysis, and systematic monitoring programs that maximize detection capabilities for subtle cometry processes despite challenging observational conditions imposed by object distance and apparent inactivity. Contemporary observational capabilities continue improving detection sensitivity while enabling better characterization of unusual objects. Tonight, every comet that develops spectacular tails during solar approach, every systematic sublimation process that creates observable gas and dust emission, every demonstration of how solar heating activates volatile compounds carries forward the memory of 3I Atlas and the ongoing puzzle of interstellar objects that resist simple classification, while challenging fundamental understanding of cometry behavior and composition through systematic deviation from expected physical processes. Trajectory analysis points to Vega through systematic orbital calculations that suggest 3I Atlas may have originated from the direction of the bright star Vega in the constellation Lyra, though its million-year journey through interstellar space creates uncertainties that complicate precise origin determination and require sophisticated mathematical analysis to account for stellar motions, galactic rotation effects, and gravitational perturbations that affect trajectory reconstruction over astronomical timescales. These origin studies represent some of the most challenging problems in celestial mechanics, where astronomers must work backward through time to reconstruct possible paths through a dynamic galactic environment where all stellar objects move according to complex gravitational interactions. Stellar motion calculations account for the systematic movement of nearby stars through three-dimensional galactic space, where proper motion measurements and radial velocity determinations enable astronomers to calculate past and future stellar positions that affect trajectory analysis of objects that may have originated near specific stellar systems millions of years ago. Vega itself moves through space at approximately 13.9 kilometers per second relative to the solar system, requiring systematic correction for stellar motion when analyzing possible gravitational interactions or origin scenarios for interstellar objects. Galactic coordinate transformation enables systematic analysis of 3I Atlas motion relative to local stellar populations and galactic structure, where trajectory analysis in galactic coordinates reveals information about the object's motion relative to the local standard of rest. and provides insights into possible origin regions within the Milky Way galaxy. These coordinate transformations account for solar system motion around the galactic center, while providing systematic frameworks for analyzing interstellar object kinematics. Only took computational trajectory analysis approximately months to establish that 3I Atlas asymptotic velocity vector, when corrected for solar gravitational deflection, points toward a region of sky near the constellation Lyra, where the bright star Vega represents the most prominent stellar system within the uncertainty ellipse of possible origin directions. Only required systematic mathematical analysis to demonstrate that trajectory reconstruction over million-year timescales involves substantial uncertainties due to unknown gravitational perturbations and stellar encounter history. Only needed comparative analysis with stellar motion data to identify Vega as a statistically probable but not definitive source region for the interstellar visitor. Gravitational perturbation analysis accounts for systematic deflections that 3I Atlas may have experienced during its interstellar journey through gravitational encounters with stellar systems, brown dwarfs, or other massive objects that could alter trajectory directions and complicate origin determination through accumulated deflection effects over million-year travel times. These perturbation effects create systematic uncertainties in trajectory reconstruction, while limiting precision of origin analysis for objects with extended interstellar travel histories. The mystery of origin uncertainty involves understanding how gravitational encounters, stellar system interactions, and galactic dynamics affect interstellar object trajectories over million-year timescales, while creating systematic limitations in precise origin determination that prevent definitive identification of formation locations or ejection mechanisms. Current mathematical methods provide statistical probability regions rather than precise origin points, while highlighting fundamental limitations in trajectory reconstruction over astronomical timescales. Stellar encounter modeling attempts to identify possible gravitational interactions between 3I Atlas and stellar systems during its interstellar journey by analyzing stellar positions and motions over the past million years, while calculating encounter probabilities and deflection effects that could influence trajectory evolution. These encounter models require sophisticated computational analysis, while providing systematic approaches for understanding trajectory modification during interstellar travel. Probability analysis techniques employ statistical methods to evaluate the likelihood that 3I Atlas originated from various stellar systems within the uncertainty region of trajectory reconstruction, accounting for stellar mass distributions, encounter cross-sections, and gravitational interaction probabilities that affect origin determination reliability. These probability calculations provide systematic frameworks for evaluating origin hypotheses while acknowledging fundamental uncertainties in trajectory reconstruction. Vega system characteristics provide context for evaluating 3I Atlas possible origin through analysis of stellar properties, planetary system architecture, and astrophysical conditions that might enable formation and ejection of interstellar objects from the Vega stellar environment. Vega represents a young, massive star with a debris disk that suggests ongoing planetary system evolution and potential for generating interstellar objects through dynamical processes. Time of flight calculations estimate the duration required for 3I Atlas to travel from possible origin regions to the solar system, while accounting for interstellar travel velocities and gravitational acceleration effects that affect journey timing and trajectory characteristics. These calculations suggest travel times of approximately 1 to several million years, depending on origin distance and trajectory assumptions, while providing constraints on formation timing and ejection mechanisms. Stellar catalog analysis systematically examines stars within the trajectory uncertainty region to identify candidate origin systems based on stellar properties, distances, proper motions, and astrophysical characteristics that might favor interstellar object formation and ejection processes. These catalogue studies provide systematic approaches for identifying probable source regions while evaluating formation mechanism hypotheses and ejection scenario models. Uncertainty propagation analysis tracks how measurement errors and theoretical assumptions affect trajectory reconstruction accuracy, while providing systematic evaluation of origin determination, reliability and confidence levels for various source region hypotheses. These uncertainty analyses provide statistical frameworks for evaluating origin claims, while acknowledging fundamental limitations in precise trajectory reconstruction over astronomical timescales. Alternative origin scenarios consider possible formation mechanisms and ejection processes that could produce 3I Atlas characteristics without requiring origin from the Vega system, including formation in stellar nurseries, ejection from binary systems, or acceleration by exotic astrophysical processes that create interstellar objects through mechanisms unrelated to specific stellar system interactions. These alternative scenarios provide systematic evaluation of formation hypotheses. Comparative trajectory analysis examines origin determinations for other interstellar objects like Oumuamua and 2I Borisov to identify systematic patterns in origin directions and evaluate whether interstellar visitors exhibit preferential source regions or random distribution patterns that provide insights into galactic interstellar object populations and transport mechanisms. These comparative studies reveal systematic characteristics of interstellar object kinematics. Future trajectory refinement opportunities may arise through improved astrometric measurements, extended observational baselines, or detection of additional interstellar objects that provide statistical samples for analyzing origin patterns and trajectory characteristics. These future capabilities would enhance origin determination accuracy while providing better understanding of interstellar object populations and galactic transport mechanisms. Observational validation techniques attempt to verify trajectory analysis through systematic comparison of predicted and observed positions, while testing mathematical models and computational methods used for origin determination and uncertainty analysis. These validation procedures provide quality control frameworks while ensuring reliability of trajectory reconstruction methods and origin determination techniques. Galactic dynamics effects on trajectory analysis include systematic consideration of galactic rotation, stellar stream motions, and large-scale gravitational influences that affect interstellar object motion over million-year timescales, while creating additional uncertainties in origin determination that supplement local stellar motion and gravitational perturbation effects. These galactic effects require sophisticated modeling while affecting trajectory, reconstruction accuracy. Modern computational methods enable systematic trajectory analysis for interstellar objects through advanced numerical integration techniques, sophisticated gravitational modeling, and statistical analysis methods that provide systematic approaches for origin determination despite fundamental uncertainties imposed by million-year travel times and complex gravitational environments. Contemporary computational capabilities continue improving trajectory analysis precision while enabling better understanding of interstellar object kinematics. Tonight, every stellar motion measurement that reveals cosmic dynamics, every mathematical analysis that reconstructs past trajectories, every demonstration of how gravitational interactions affect celestial mechanics carries forward the legacy of 3I Atlas and the systematic quest to understand cosmic origins through trajectory analysis that connects interstellar visitors with their distant formation environments across the vast scales of galactic space and geological time. The technology gap in detection highlights fundamental limitations in current astronomical survey capabilities that enable only a small fraction of interstellar visitors to be identified during their brief passages through the solar system, with 3i Atlas Discovery emphasizing both the success and constraints of existing detection methods, while revealing the likelihood that many cosmic visitors pass through undetected due to observational limitations, insufficient sky coverage, and technological constraints that affect our ability to systematically monitor the solar system for exotic objects. This detection challenge represents one of the most significant frontiers in contemporary astronomy, where improving survey capabilities could revolutionize understanding of interstellar object populations and galactic material exchange processes. Survey sensitivity limitations restrict current detection capabilities to objects that achieve sufficient brightness and exhibit motion characteristics that trigger automated detection algorithms within existing astronomical monitoring programs. Most current surveys focus on potentially hazardous near-Earth asteroids and operate with sensitivity thresholds that may miss smaller interstellar objects, or those following trajectories that don't bring them close enough to Earth for easy detection. These sensitivity constraints create systematic biases in detected interstellar object populations, while potentially missing representative samples of galactic visitors. Sky coverage constraints affect interstellar object detection through limitations in telescopic field of view and observational cadence that prevent comprehensive monitoring of all directions from which cosmic visitors might approach the solar system. Current survey programs typically focus on ecliptic regions where most potentially hazardous asteroids concentrate, potentially missing interstellar objects approaching from high galactic latitudes or unusual trajectory orientations that don't coincide with traditional asteroid survey priorities. Only took 3 Atlas approximately years to traverse observable regions of the solar system, while remaining detectable with current telescopic capabilities, emphasizing the brief observational windows available for interstellar object study and the time pressure that affects comprehensive characterization efforts. Only required systematic analysis of detection statistics to demonstrate that current survey capabilities likely miss most interstellar visitors due to sensitivity limitations, sky coverage constraints, and cadence restrictions that affect detection probability. Only needed comparative analysis with theoretical population models to suggest that detected interstellar objects represent a small fraction of actual visitors passing through the solar system. Automated detection algorithms rely on systematic image comparison and motion detection techniques that identify moving objects through analysis of sequential observations taken hours or days apart. But these algorithms require optimization for interstellar object characteristics that may differ from traditional solar system objects in brightness, motion patterns, and trajectory orientations. Current detection algorithms optimize for near-Earth asteroid characteristics while potentially missing interstellar objects with unusual photometric or kinematic properties. The mystery of population statistics involves understanding the true frequency of interstellar object passages through the solar system based on limited detection samples that may not represent actual visitor populations due to systematic observational biases and detection limitations. Statistical extrapolation from detected objects suggests interstellar visitor rates that range from several per year to several per decade. But these estimates remain highly uncertain due to small sample sizes and unknown detection biases. Brightness threshold effects create systematic detection limitations, where only interstellar objects that achieve sufficient apparent magnitude can be detected with current telescopic capabilities, potentially missing entire populations of smaller objects that might provide different insights into interstellar object formation and galactic material exchange processes. These brightness thresholds depend on object size, surface reflectivity, solar distance, and observational geometry, while creating systematic biases toward larger or more reflective objects. Trajectory bias considerations account for systematic detection preferences for interstellar objects following specific types of orbits that bring them close to Earth or the Sun, while potentially missing objects with different trajectory characteristics that remain more distant or approach from directions that receive less observational coverage. These trajectory biases affect statistical interpretation of interstellar object populations, while creating systematic uncertainties in frequency estimates and characteristic determinations. Observational cadence limitations affect detection capability when survey programs employ observation schedules that may miss rapidly moving interstellar objects or those with brightness variations that don't match survey timing patterns. Most current surveys operate with cadences optimized for traditional solar system objects, while potentially missing interstellar visitors with different temporal characteristics or motion patterns that require alternative observation strategies. Technological improvements in detection capability include development of wider field telescopes, more sensitive detectors, improved automated analysis algorithms, and systematic survey strategies specifically designed for interstellar object detection, rather than adaptation of existing near-Earth asteroid survey methods. These technological advances could dramatically improve detection rates while enabling better characterization of interstellar object populations and their statistical properties. False positive management represents a significant challenge in interstellar object detection, where unusual solar system objects, observational artifacts, or measurement errors can mimic interstellar object characteristics, while requiring systematic verification procedures that distinguish genuine visitors from false detections. These verification requirements affect detection efficiency, while emphasizing the importance of systematic confirmation procedures and international collaboration in interstellar object identification. Survey coordination between multiple telescopic facilities could enhance interstellar object detection through systematic sky coverage optimization, complementary observation strategies, and rapid follow-up capabilities that maximize detection probability while enabling comprehensive characterization during brief observational windows. These coordination efforts require international cooperation while providing systematic approaches for optimizing limited observational resources. Machine learning applications to interstellar object detection employ advanced pattern recognition techniques and artificial intelligence algorithms that could improve detection sensitivity and reduce false positive rates through systematic analysis of large astronomical datasets and identification of subtle characteristics that distinguish interstellar objects from solar system populations. These machine learning approaches provide systematic frameworks for enhancing detection capabilities. Space-based survey advantages include elimination of atmospheric limitations, continuous observation capabilities, and access to infrared wavelengths that provide enhanced detection sensitivity and reduced observational constraints compared to ground-based surveys. Space-based platforms could revolutionize interstellar object detection while providing systematic monitoring capabilities that exceed ground-based limitations and atmospheric interference effects. Real-time alert systems enable rapid notification of potential interstellar object detections to facilitate immediate follow-up observations and comprehensive characterization efforts during limited observational windows. These alert systems require systematic communication protocols and coordinated response capabilities that maximize scientific return from brief detection opportunities while enabling international collaboration and resource optimization. Statistical modeling of detection efficiency attempts to quantify current survey capabilities and estimate the fraction of interstellar objects that remain undetected due to various observational limitations and technological constraints. These statistical models provide systematic frameworks for interpreting detection rates, while extrapolating to actual interstellar object populations and frequencies that may differ significantly from detected samples. Future survey capabilities through next-generation telescopes and improved detection systems could enhance interstellar object discovery rates by orders of magnitude while enabling better statistical characterization of visitor populations and more comprehensive understanding of galactic material exchange processes. These future capabilities would revolutionize interstellar object research while providing systematic databases for comparative analysis and theoretical modeling. International collaboration requirements for comprehensive interstellar object detection involve coordinated survey strategies, shared observational resources, and systematic data-sharing protocols that optimize global detection capabilities while ensuring rapid follow-up observations and comprehensive characterization efforts. These collaboration frameworks provide systematic approaches for maximizing detection efficiency through international cooperation and resource coordination. Modern survey technology continues advancing detection capabilities through improved telescope designs, enhanced detector sensitivity, and sophisticated data analysis techniques that provide systematic improvements in interstellar object detection, while enabling better characterization of cosmic visitors and their populations. Contemporary technological developments continue expanding detection capabilities while revealing the scope of interstellar object populations. Tonight, every automated survey that scans the night sky, every detection algorithm that identifies moving objects, every systematic effort to monitor cosmic visitors carries forward the legacy of 3i Atlas and the ongoing challenge of comprehensive interstellar object detection that could revolutionize understanding of galactic material exchange through technological advances that enable systematic monitoring of cosmic visitors from distant stellar systems. Comparative analysis with Oumuamua reveals both striking similarities and crucial differences between the first and third confirmed interstellar objects, where systematic comparison of physical characteristics, orbital properties, and observational behavior creates a framework for understanding interstellar object diversity, while identifying common features that may reflect shared formation mechanisms or evolutionary processes operating in distant stellar systems. This comparative approach provides essential scientific methodology for distinguishing individual object peculiarities from systematic characteristics that define interstellar visitor populations, enabling theoretical modeling of formation processes and galactic material exchange mechanisms. Physical property comparisons between 3 Atlas and Oumuamua reveal systematic differences in size estimates, brightness variations, and apparent composition, while both objects share fundamental characteristics, including hyperbolic trajectories, minimal cometary activity, and unusual photometric behavior that distinguishes them from typical solar system comets and asteroids. These comparative studies provide systematic frameworks for identifying interstellar object characteristics while revealing diversity within the limited sample of confirmed cosmic visitors. Trajectory analysis comparisons demonstrate that both 3 Atlas and Oumuamua follow hyperbolic orbits with eccentricities significantly exceeding unity, confirming their interstellar origins while revealing different approach velocities, perihelion distances, and asymptotic velocity vectors that suggest distinct formation locations and gravitational histories during their journeys through galactic space. These trajectory differences provide insights into the diversity of interstellar object source regions and acceleration mechanisms. Only took systematic comparative analysis approximately months to establish that 3I Atlas and Oumuamua share fundamental interstellar characteristics, while exhibiting individual differences that suggest diversity in formation mechanisms, composition, and evolutionary histories among objects ejected from different stellar systems, or formed under varying astrophysical conditions. Only required detailed comparison of observational data to reveal both commonalities and distinctions that inform theoretical understanding of interstellar object populations. Only needed systematic analysis to demonstrate that confirmed interstellar objects exhibit both shared and unique characteristics that provide insights into galactic material exchange processes. Compositional comparison attempts reveal systematic challenges in determining surface materials for both objects, where spectroscopic analysis provides limited constraints on composition, while suggesting that neither object exhibits obvious similarities to typical solar system asteroid or comet materials. These compositional uncertainties affect comparative analysis, while highlighting observational limitations that prevent definitive material identification for small, distant interstellar objects with potentially exotic surface properties. The mystery of behavioral diversity involves understanding why some confirmed interstellar objects like 2I Borisov exhibit obvious cometary activity, while others like Oumuamua and 3I Atlas show minimal outgassing despite solar heating that should activate volatile sublimation in typical cometary materials. This behavioral diversity suggests fundamental differences in composition, formation mechanisms, or evolutionary processing that create distinct populations within interstellar object communities. Brightness variation patterns differ systematically between 3 Atlas and Oumuamua, where both objects exhibit complex photometric behavior that challenges conventional rotation analysis, but display different variation amplitudes, timescales, and pattern characteristics that suggest distinct geometric properties or surface composition effects. These photometric differences provide insights into individual object characteristics, while revealing diversity in interstellar object physical properties. Size determination challenges affect both objects through similar observational limitations imposed by small apparent size, uncertain surface reflectivity, and complex geometric properties that create systematic ambiguities in dimension estimates. Comparative size analysis reveals that both objects likely represent relatively small bodies measuring tens to hundreds of meters in characteristic dimension, but precise size determination remains limited by albedo uncertainties and shape complexity. Acceleration anomalies represent another point of comparison where Oumuamua exhibited systematic non-gravitational acceleration that generated scientific controversy, while 3 Atlas shows no obvious acceleration anomalies within observational precision limits. These acceleration differences suggest distinct physical processes or object properties that affect motion characteristics while providing constraints on theoretical models of interstellar object behavior. Origin analysis comparisons reveal that trajectory reconstruction suggests different source regions for 3I Atlas and Oumuamua, with systematic analysis pointing toward distinct stellar neighborhoods that may reflect either different formation locations or different gravitational interaction histories during interstellar travel. These origin differences provide insights into galactic interstellar object transport, while suggesting diversity in source regions and ejection mechanisms. Observational constraint similarities affect both objects through comparable challenges including limited observation windows, small apparent size, rapid motion, and insufficient brightness for detailed spectroscopic analysis. creating systematic limitations that affect comparative studies and theoretical interpretation of interstellar object characteristics. These observational constraints highlight technological limitations while emphasizing the need for improved detection and characterization capabilities. Statistical significance considerations account for the limited sample size of confirmed interstellar objects when drawing conclusions about population characteristics and systematic behaviors. Where comparisons between individual objects provide preliminary insights, while requiring larger samples for reliable statistical analysis of interstellar visitor populations and their defining characteristics. Current sample limitations affect theoretical understanding while motivating continued detection efforts. Theoretical modeling applications use comparative analysis between 3I Atlas and Oumuamua to test formation hypotheses and evolutionary scenarios while providing observational constraints that guide theoretical development and validate or refute specific models of interstellar object formation, composition, and galactic transport processes. These theoretical applications demonstrate the scientific value of systematic comparative analysis despite limited sample sizes. Formation mechanism hypotheses attempt to explain observed similarities and differences between confirmed interstellar objects through theoretical models of planetary system evolution, gravitational ejection processes, and stellar system dynamics that could produce objects with characteristics matching observational constraints, while accounting for diversity in physical properties and behavioral characteristics. Detection bias effects may influence comparative analysis by creating systematic preferences for specific types of interstellar objects, while potentially missing populations with different characteristics, leading to apparent similarities or differences that reflect observational limitations rather than actual population properties. These detection biases require careful consideration when interpreting comparative studies and extrapolating to broader interstellar object populations. Future comparative opportunities will arise as additional interstellar objects are detected and characterized, providing larger samples that enable more reliable statistical analysis of population characteristics while reducing the influence of individual object peculiarities on theoretical understanding of interstellar visitor properties and formation mechanisms. These future studies would enhance comparative analysis while providing better constraints on theoretical models. Systematic database development for interstellar object characteristics enables organized storage and analysis of comparative data while providing standardized frameworks for future comparative studies and theoretical modeling applications that require systematic access to observational constraints and physical property measurements for confirmed cosmic visitors. International collaboration in comparative analysis facilitates sharing of observational data, theoretical insights, and analysis techniques while ensuring comprehensive characterization of confirmed interstellar objects through coordinated observational campaigns and systematic data reduction procedures that maximize scientific return from limited detection opportunities. Modern comparative analysis techniques employ sophisticated statistical methods, systematic database management, and advanced theoretical modeling that provide systematic frameworks for understanding interstellar object diversity, while identifying common characteristics that define visitor populations and inform theoretical understanding of galactic material exchange processes and formation mechanisms. Tonight, every systematic comparison that reveals cosmic patterns, every careful analysis that distinguishes individual from universal characteristics, every demonstration of how comparative studies advance scientific understanding carries forward the legacy of 3I Atlas and Oumuamua through systematic approaches to interstellar object research that transform limited observations into comprehensive understanding of cosmic visitors and their diverse origins in distant stellar systems. The formation theories multiply as astronomers grapple with explaining 3I Atlas's enigmatic characteristics through various hypotheses that range from conventional planetary system ejection mechanisms to exotic scenarios involving stellar collisions, brown dwarf encounters, and formation processes operating under astrophysical conditions that differ fundamentally from solar system environments. These theoretical proliferation reflects both the object's unusual properties and the limited observational constraints available for testing formation models, creating scientific uncertainty that motivates diverse theoretical approaches while highlighting fundamental gaps in understanding interstellar object origins and galactic material exchange processes. Planetary ejection scenarios propose that 3I Atlas originated as a conventional asteroid or comet within a distant planetary system before experiencing gravitational scattering by massive planets that accelerated the object beyond escape velocity through systematic energy transfer during close encounters. These ejection models rely on well-understood gravitational dynamics, while requiring specific geometric and timing conditions that occur during planetary system evolution, particularly during early chaotic phases when planetary orbits remain unstable and gravitational interactions achieve maximum intensity. Stellar formation region dispersal represents another formation pathway, where 3I Atlas could have originated during the dissolution of stellar nurseries, when young stellar systems separate and disperse throughout galactic space, carrying with them populations of small bodies that become unbound from their parent stars through reduced gravitational binding as stellar clusters expand and individual stars begin independent galactic orbits. These dispersal scenarios explain interstellar object formation through systematic stellar cluster evolution rather than violent ejection processes. Only took theoretical modeling approximately years to generate multiple plausible formation hypotheses for 3I Atlas characteristics through systematic analysis of planetary dynamics, stellar evolution, and galactic material transport processes that could produce objects with observed physical properties and kinematic characteristics. Only required comparative analysis with known astrophysical processes to identify potential formation mechanisms that remain consistent with observational constraints and theoretical understanding of stellar system evolution. Only needed systematic evaluation of various formation scenarios to demonstrate that multiple pathways could potentially explain interstellar object characteristics. Brown dwarf interaction models suggest that 3I Atlas may have experienced gravitational encounters with substellar objects that provided acceleration mechanisms through close approach dynamics, where brown dwarfs wandering through interstellar space could create gravitational perturbations sufficient to accelerate small bodies to interstellar travel velocities. These brown dwarf scenarios require specific encounter geometries, while providing alternative acceleration mechanisms that operate independently of conventional planetary system dynamics. The mystery of formation environment diversity involves understanding how different stellar formation conditions, planetary system architectures, and galactic environments might produce interstellar objects with varying characteristics, while creating populations of cosmic visitors that reflect the diversity of formation processes operating throughout the Milky Way galaxy. Current theoretical understanding provides limited constraints on formation, environment effects, while highlighting uncertainties in interstellar object formation modeling. Stellar collision aftermath scenarios propose that 3I Atlas could represent debris generated during stellar mergers, close stellar encounters, or other high-energy astrophysical events that create extreme gravitational conditions capable of accelerating planetary materials to interstellar velocities through systematic energy transfer during stellar system disruption. These collision models require rare astrophysical events while providing energy sources sufficient for interstellar object acceleration. Binary system evolution provides additional formation pathways through gravitational instabilities that develop when binary stellar systems undergo orbital evolution, mass transfer, or stellar evolution phases that create systematic changes in gravitational binding and enable ejection of orbiting materials through three-body gravitational interactions. These binary scenarios explain interstellar object formation through systematic stellar evolution processes rather than external perturbations. Galactic tide effects may contribute to 3I Atlas formation through systematic gravitational influences from galactic structure that affect stellar system stability and enable ejection of weakly bound materials during passages through galactic spiral arms, stellar cluster encounters, or other large-scale gravitational environments that create periodic perturbations affecting planetary system integrity. Chemical composition constraints from spectroscopic analysis provide observational tests for formation theories by revealing surface material characteristics that must remain consistent with proposed formation environments and processing histories. These compositional constraints eliminate formation scenarios that would produce materials incompatible with observed spectral characteristics, while supporting theories that predict appropriate chemical signatures. Dynamical modeling techniques employ sophisticated computational simulations that test various formation scenarios through systematic analysis of gravitational interactions, orbital evolution, and energy transfer processes operating under different astrophysical conditions. These modeling studies provide quantitative evaluation of formation hypothesis viability while identifying parameter ranges that produce objects with characteristics matching observational constraints. Population synthesis models attempt to predict interstellar object characteristics and frequencies based on different formation mechanisms, while providing statistical frameworks for evaluating which formation processes could produce observed interstellar visitor populations. These synthesis models combine theoretical formation scenarios with galactic structure and stellar evolution to predict detectable interstellar object rates and characteristics. Observational validation approaches identify specific observational signatures or measurements that could distinguish between competing formation theories, while guiding future observational strategies designed to test theoretical predictions and constrain formation mechanism hypotheses. These validation frameworks provide systematic approaches for using limited observational data to evaluate theoretical models and formation scenarios. Multi-object analysis employs comparative studies of multiple confirmed interstellar objects to identify systematic patterns in physical properties, trajectory characteristics, and behavioral features that provide constraints on formation mechanisms, while revealing whether different formation processes produce objects with distinguishable observational signatures. These comparative approaches enhance theoretical understanding through systematic analysis of limited samples. Temporal evolution considerations account for processing and modification that 3I Atlas may have experienced during millions of years of interstellar travel, where cosmic ray bombardment, thermal cycling, and chemical weathering could alter original formation signatures while creating observational characteristics that differ from initial formation properties. These evolution effects complicate formation theory testing while requiring systematic consideration of post-formation processing. Statistical evaluation methods provide systematic frameworks for comparing formation theory predictions with observational constraints while accounting for measurement uncertainties and theoretical model limitations that affect hypothesis testing and theory validation. These statistical approaches enable objective evaluation of competing formation scenarios despite limited observational data and theoretical uncertainties. Future observational opportunities for testing formation theories may arise through detection of additional interstellar objects, improved characterization techniques, or potential sample return missions that could provide definitive constraints on formation mechanisms through direct material analysis and detailed physical property determination. These future capabilities would revolutionize formation theory validation while providing definitive answers to current theoretical uncertainties. Interdisciplinary approaches to formation theory development combine insights from planetary science, stellar astrophysics, galactic dynamics, and observational astronomy to create comprehensive theoretical frameworks that account for multiple astrophysical processes while providing systematic understanding of interstellar object formation within broader contexts of stellar and galactic evolution. Modern theoretical methods enable sophisticated formation modeling through advanced computational techniques, systematic parameter space exploration, and integration of multiple astrophysical processes that provide comprehensive theoretical frameworks for understanding interstellar object formation, while guiding observational strategies designed to test theoretical predictions and constrain formation mechanisms. Tonight, every theoretical model that explains cosmic phenomena, every systematic hypothesis that connects observations with physical processes, every demonstration of how multiple formation pathways could produce similar results, carries forward the legacy of 3's Atlas, and the ongoing quest to understand cosmic origins through theoretical diversity that acknowledges observational limitations while exploring multiple formation scenarios that could explain the exotic characteristics of visitors from distant stellar systems. Observational challenges and time pressure create systematic constraints that test the limits of contemporary astronomical capabilities as astronomers race against the relentless orbital mechanics that carry 3 Atlas away from the inner solar system at velocities exceeding 40 kilometers per second, providing only a brief window of opportunity for detailed scientific study before the object becomes too faint and distant for further observation with current telescopic technology. This time pressure represents one of the most significant challenges in interstellar object research, where the same hyperbolic trajectories that prove interstellar origin also guarantee that observational opportunities remain frustratingly brief and unrepeatable. Brightness decline effects systematically reduce observational capabilities as 3i Atlas increases its distance from both Earth and the Sun while following its hyperbolic trajectory toward interstellar space, creating predictable but relentless reductions in apparent brightness that follow inverse square law relationships for both solar illumination and Earth object distance. These brightness declines create systematic observation scheduling pressures, where telescope time allocation decisions must balance immediate observational needs against rapidly diminishing future opportunities for data collection. Distance-velocity relationships govern the systematic expansion of Earth object separation that affects not only brightness, but also angular motion rates, spectroscopic resolution, and photometric precision through geometric effects that compound observational difficulties as 3i Atlas continues its journey away from the solar system. These geometric constraints create systematic degradation of observational quality that affects all measurement techniques, while emphasizing the critical importance of early detection and immediate observational response. Only took 3i Atlas approximately 18 months from discovery to become too faint for detailed spectroscopic analysis with most ground-based telescopes. demonstrating the brief observational windows available for comprehensive interstellar object characterization through systematic analysis of brightness, decline and distance increase effects. Only required systematic observation scheduling to establish that priority. Observational programs must begin immediately upon detection, while coordinating international telescope resources to maximize data collection during limited accessibility periods. Only needed careful time management to complete essential observational objectives before objects become observationally inaccessible. Telescope allocation challenges arise when multiple research groups compete for limited observational resources, while 3D Atlas remains accessible for study, creating systematic pressures on telescope scheduling and scientific priority decisions that must balance various research objectives against diminishing observational opportunities. These allocation decisions require international coordination and rapid response capabilities that exceed normal astronomical observation planning timescales. The mystery of observation prioritization involves determining which measurements and analysis techniques provide maximum scientific return during limited observational windows while accounting for weather uncertainties, instrument limitations, and competing observational demands that affect data collection efficiency. Current observational strategies rely on systematic prioritization protocols that attempt to optimize scientific return despite uncertain observational conditions and time constraints. Weather dependency effects create additional uncertainties in observational planning where cloud coverage, atmospheric turbulence, and seasonal weather patterns introduce systematic risks that could eliminate critical observational opportunities during brief windows when interstellar objects remain accessible for study. These weather risks require backup observational strategies and global telescope coordination that provide redundancy against local, weather-related observational failures. Instrumental sensitivity limitations become increasingly important as 3i Atlas brightness declines, where measurements that remained feasible during early detection phases become impossible as signal-to-noise ratios decline below usable thresholds, despite increased telescope exposure times and sophisticated data reduction techniques. These sensitivity constraints create systematic trade-offs between measurement precision and observational feasibility that affect scientific planning and data collection strategies. Atmospheric interference effects supplement instrumental limitations through systematic degradation of observational quality caused by atmospheric turbulence, absorption, and scattering that become more significant as objects become fainter and require longer exposure times for adequate signal detection. These atmospheric effects create additional constraints on ground-based observations, while highlighting advantages of space-based telescopic platforms for faint object studies. International coordination requirements become critical for maximizing observational return from limited time windows through systematic collaboration between observatories worldwide that provide continuous coverage and complementary observational capabilities despite individual site limitations imposed by weather, instrumental characteristics, and geographic constraints. These coordination efforts require rapid communication and flexible scheduling that exceed normal astronomical collaboration protocols. Data reduction urgency creates systematic pressures on astronomical data processing and analysis procedures, where rapid turnaround becomes essential for guiding subsequent observational decisions and optimizing remaining observational opportunities before objects become inaccessible. These processing pressures require streamlined analysis procedures and automated data reduction techniques that provide timely feedback for observational planning. Follow-up observation strategies attempt to optimize scientific return through systematic observation scheduling that balances various measurement objectives while accounting for declining observational feasibility and competing resource demands. These strategies require careful planning that anticipates observational constraints while maintaining flexibility for responding to preliminary results and unexpected discoveries during brief accessibility periods. Target of opportunity protocols enable rapid telescope response to interstellar object detections through pre-approved observational programs and streamlined approval procedures that minimize bureaucratic delays during time-critical observational windows. These protocols provide systematic frameworks for immediate observational response while ensuring quality control and scientific coordination despite compressed decision-making timescales. Archive value considerations emphasize the long-term scientific importance of comprehensive data collection during brief observational opportunities, where systematic documentation and data preservation become essential for future analysis and reanalysis as theoretical understanding advances and analysis techniques improve. These archival considerations motivate comprehensive data collection despite immediate analysis limitations and resource constraints. Technological limitations in current observational capabilities highlight systematic constraints that affect interstellar object characterization, while motivating development of improved detection systems, more sensitive instruments, and enhanced data analysis techniques designed specifically for rapid characterization of transient astronomical phenomena. These limitations provide guidance for future technological development priorities and observational strategy optimization. Multi-wavelength coordination enables comprehensive characterization through simultaneous observations across various wavelength ranges that provide complementary information about physical properties while maximizing scientific return during limited observational windows. These multi-wavelength approaches require sophisticated coordination while providing systematic frameworks for comprehensive object characterization despite time constraints. Rapid publication strategies ensure timely dissemination of observational results and theoretical interpretations that enable international scientific community participation in interstellar object research, while providing systematic knowledge sharing that enhances collective understanding despite individual observational limitations and resource constraints. These publication strategies balance scientific rigor with time pressure requirements. Space-based observation advantages include elimination of weather dependencies, continuous observational access, and enhanced sensitivity that could revolutionize interstellar object characterization through systematic improvements in observational capabilities and reduced environmental constraints. These space-based platforms provide systematic solutions to many ground-based observational limitations, while enabling extended monitoring capabilities. Future preparedness initiatives develop systematic frameworks for rapid response to future interstellar object detections through improved survey capabilities, enhanced international coordination protocols, and pre-planned observational strategies that optimize scientific return during brief accessibility windows. These preparedness efforts provide systematic approaches for maximizing future scientific opportunities while building upon lessons learned from current interstellar object studies. Modern observational techniques continue advancing rapid characterization capabilities through improved instruments, sophisticated data analysis methods, and systematic coordination protocols that provide enhanced scientific return despite fundamental time constraints imposed by interstellar object orbital dynamics. Contemporary technological developments enable more efficient use of limited observational opportunities while expanding characterization capabilities for exotic astronomical phenomena. Tonight, every carefully scheduled observation that maximizes scientific return, every international collaboration that shares limited resources, Every demonstration of how time pressure motivates observational innovation carries forward the legacy of 3E Atlas and the ongoing challenge of comprehensive astronomical characterization within brief observational windows that test the limits of contemporary astronomical capabilities while motivating technological development and international cooperation. What 3E Atlas teaches about galactic evolution emerges through systematic analysis of how interstellar objects serve as natural probes of planetary formation processes around other stars, providing direct physical samples of materials that formed under different stellar conditions while carrying chemical and isotopic signatures that reveal information about stellar nucleosynthesis, planetary system architecture, and dynamical evolution in diverse galactic environments. These cosmic messengers represent unique scientific opportunities to study comparative planetology on galactic scales, where analysis of visitor characteristics provides insights into formation processes operating around different stellar types in various galactic locations, and under astrophysical conditions that may differ systematically from solar system formation environments. Stellar nucleosynthesis signatures preserved within 3I Atlas materials could potentially reveal information about the chemical evolution of distant stellar systems through isotopic ratios and elemental abundances that reflect the nuclear processes operating within different stellar types during planetary system formation. These nucleosynthesis signatures provide systematic information about stellar evolution and chemical enrichment processes operating in galactic regions with different star formation histories and metallicity distributions that affect planetary formation chemistry. Planetary formation diversity becomes accessible through comparative analysis of interstellar object characteristics that reveal how planetary system assembly processes might vary between different stellar environments, where systematic differences in composition, structure, and formation mechanisms provide insights into the range of planetary formation outcomes operating throughout the galaxy. These formation studies enable systematic comparison between solar system formation and alternative planetary formation pathways. Only took 3I Atlas analysis approximately years to demonstrate that interstellar objects provide unique opportunities for studying galactic planetary formation diversity through direct examination of materials that formed around different stars under potentially different astrophysical conditions. Only required systematic comparison with solar system materials to reveal chemical and physical signatures that suggest formation under conditions that may differ from local stellar neighborhood chemistry and dynamics. Only needed theoretical modeling to establish that interstellar visitors provide natural laboratories for studying comparative planetology across galactic scales. Chemical evolution studies utilize 3I Atlas compositional analysis to understand how stellar chemical enrichment affects planetary formation through systematic examination of elemental abundances and isotopic ratios that reflect the chemical history of different galactic regions and stellar populations. These chemical studies provide insights into galactic chemical evolution, while revealing how stellar metallicity and chemical composition affect planetary system formation processes and material characteristics. The mystery of galactic material transport involves understanding how interstellar objects contribute to chemical and isotopic mixing between stellar systems, while serving as vectors for galactic material exchange that could affect chemical evolution and stellar system development through systematic transport of processed materials across galactic distances. Current models suggest that interstellar object populations could provide significant material exchange mechanisms operating over galactic timescales. Stellar system archaeology becomes possible through detailed analysis of 3I Atlas characteristics that preserve information about formation conditions, dynamical history, and evolutionary processing that occurred within distant stellar systems millions of years ago. These archaeological studies provide systematic approaches for reconstructing planetary system evolution and understanding formation mechanisms that operated under different astrophysical conditions than contemporary solar system observations. Dynamical evolution insights emerge from 3I Atlas trajectory analysis and physical characteristics that provide information about gravitational processes, orbital evolution, and instability mechanisms operating within distant planetary systems during various evolutionary phases. These dynamical studies reveal systematic patterns in planetary system evolution while providing constraints on theoretical models of long-term orbital stability and system architecture development. Galactic structure effects on planetary formation become accessible through systematic analysis of interstellar object characteristics that reflect formation conditions in different galactic environments, where variations in stellar density, metallicity gradients, and galactic dynamics could affect planetary formation processes while creating systematic differences in material properties and formation mechanisms across galactic locations. Temporal evolution studies utilize 3I Atlas characteristics to understand how planetary formation processes may have changed over galactic history through analysis of formation signatures that reflect stellar system ages and formation epochs. These temporal studies provide insights into galactic evolution while revealing how changing galactic conditions affect planetary formation processes and stellar system development over billion-year timescales. Comparative planetology applications employ 3I Atlas analysis to understand universal versus local aspect of planetary formation through systematic comparison with solar system formation models and observational constraints. These comparative studies reveal which planetary formation processes represent universal astrophysical mechanisms versus local environmental effects specific to solar system formation conditions and stellar neighborhood characteristics. Statistical population analysis attempts to characterize galactic interstellar object populations through analysis of detection rates, characteristic distributions, and physical properties that provide insights into the frequency and diversity of planetary formation outcomes operating throughout the galaxy. These population studies require systematic consideration of observational biases while providing statistical frameworks for understanding galactic planetary formation efficiency. Formation mechanism constraints emerge from 3I Atlas characteristics that provide observational tests for theoretical models of planetary formation, gravitational dynamics, and stellar system evolution operating under different astrophysical conditions. These constraint studies enable systematic evaluation of formation theories while identifying universal formation mechanisms versus environment-specific processes that affect planetary system development. Astrobiology implications arise from 3I Atlas studies that provide insights into the diversity of planetary formation processes and material characteristics that could affect habitability and biological potential in different stellar environments. These astrobiological applications utilize interstellar object analysis to understand formation conditions that favor or inhibit biological development, while providing systematic frameworks for evaluating habitability across galactic scales. Galactic chemical inventory studies employ interstellar object analysis to understand the distribution and transport of chemical elements throughout the galaxy, while providing insights into chemical enrichment processes and material cycling that affect stellar and planetary formation over galactic evolution timescales. These inventory studies reveal systematic patterns in galactic chemical evolution, while providing constraints on chemical mixing and transport mechanisms. theoretical model validation utilizes 3I Atlas characteristics to test theoretical predictions about planetary formation, galactic evolution, and stellar system development through systematic comparison between observational constraints and theoretical model predictions. These validation studies provide systematic approaches for evaluating theoretical frameworks while identifying areas where current understanding requires modification or development. Future research opportunities through additional interstellar object detections would enhance understanding of galactic evolution through larger statistical samples that enable systematic characterization of interstellar visitor populations, while providing better constraints on formation mechanisms and galactic material transport processes. These future studies would revolutionize understanding of galactic planetary formation diversity and chemical evolution processes. Multi-object comparative analysis enables systematic study of galactic evolution through comparative analysis of multiple interstellar visitors that reveal systematic patterns in formation processes, material characteristics, and dynamical evolution, while providing statistical frameworks for understanding galactic planetary formation diversity and chemical enrichment mechanisms. Interdisciplinary integration combines interstellar object research with galactic astronomy, stellar evolution studies, and theoretical planetology to create comprehensive understanding of galactic evolution through systematic integration of observational constraints and theoretical frameworks that connect local solar system formation with galactic-scale planetary formation processes. Modern galactic evolution research incorporates interstellar object studies into broader frameworks for understanding galactic chemical evolution, stellar formation history, and planetary system development through systematic analysis that connects small-scale planetary formation processes with large-scale galactic evolution mechanisms and chemical enrichment patterns. Tonight, every insight into planetary formation diversity, every measurement that reveals galactic chemical evolution, every demonstration of how local processes connect with galactic-scale phenomena carries forward the legacy of 3I Atlas and the systematic quest to understand our galaxy's evolution through direct study of cosmic visitors that serve as natural ambassadors from distant stellar systems, bringing fragments of alien worlds within reach of terrestrial analysis and human understanding. The future of interstellar object research, catalyzed by 3I Atlas discovery, promises revolutionary advances in detection capabilities, characterization techniques, and theoretical understanding that could transform our comprehension of galactic material exchange while establishing systematic frameworks for studying planetary formation diversity across stellar populations throughout the Milky Way galaxy. The scientific momentum generated by early interstellar object detections motivates development of dedicated survey systems, advanced analytical techniques, and ambitious space missions designed specifically for intercepting and studying cosmic visitors during their brief passages through the solar system. Next-generation survey capabilities under development include wide-field telescopes with enhanced sensitivity and automated detection algorithms specifically optimized for interstellar object characteristics, where systematic improvements in sky coverage, photometric precision, and rapid response protocols could increase detection rates by orders of magnitude while enabling real-time identification and immediate observational follow-up. These advanced survey systems incorporate lessons learned from early interstellar object discoveries while addressing observational limitations that currently prevent comprehensive monitoring of cosmic visitor populations. Space-based detection platforms offer revolutionary advantages through elimination of atmospheric interference, continuous observational access, and enhanced infrared sensitivity that could detect smaller and more distant interstellar objects while providing extended monitoring capabilities that exceed ground-based limitations. These space-based systems enable systematic characterization throughout entire solar system passages while providing thermal infrared observations that determine size and composition independent of surface reflectivity assumptions. Only took 3I Atlas research approximately years to catalyze development of systematic frameworks for interstellar object science that guide future observational strategies, theoretical modeling priorities, and technological development goals designed to maximize scientific return from cosmic visitor studies. Only required analysis of observational challenges and scientific opportunities to identify critical technology needs and research priorities that could revolutionize interstellar object characterization capabilities. Only needed systematic evaluation of current limitations to establish development roadmaps for advanced detection and analysis systems. Rapid response protocols emerging from 3I Atlas experience emphasize automated detection notification systems, pre-approved observational programs, and international coordination mechanisms that minimize response delays during time-critical observational windows. These response systems incorporate real-time alert networks and streamlined decision-making procedures that enable immediate telescope allocation and coordinated multi-wavelength observations during brief accessibility periods. The mystery of population statistics drives development of systematic detection programs designed to characterize interstellar visitor frequency, size distributions, and characteristic properties through statistical analysis of larger object samples that could reveal fundamental patterns in galactic material exchange and planetary formation processes. Current detection limitations prevent reliable population characterization while motivating development of comprehensive survey capabilities. Interception mission concepts propose ambitious space missions designed to rendezvous with interstellar objects for detailed in situ analysis through spacecraft that could provide close-range observations, sample collection, and comprehensive characterization impossible through remote sensing techniques. These interception missions require advanced propulsion systems and autonomous navigation capabilities while offering unprecedented scientific opportunities for direct interstellar object analysis. Theoretical modeling advances incorporate insights from early interstellar object studies into sophisticated computational frameworks that predict visitor characteristics, formation mechanisms, and galactic transport processes while providing systematic approaches for interpreting observational data and guiding future research priorities. These theoretical developments enable systematic integration of interstellar object research with broader astrophysical understanding. Multi-wavelength characterization techniques under development combine visible, infrared, radio, and potentially X-ray observations to provide comprehensive physical and chemical characterization that maximizes information extraction during limited observational opportunities. These multi-wavelength approaches require sophisticated instrumental coordination while providing systematic frameworks for complete object characterization despite observational time constraints. Machine learning applications to interstellar object research employ artificial intelligence algorithms for automated detection, classification, and analysis that could dramatically improve identification efficiency while enabling systematic pattern recognition and comparative analysis across large data sets of cosmic visitor observations. These machine learning approaches provide systematic frameworks for handling large data volumes while identifying subtle characteristics that distinguish interstellar objects. International collaboration frameworks emerging from 3I Atlas research establish systematic protocols for coordinated observational campaigns, data sharing, and collaborative analysis that maximize scientific return through global cooperation while ensuring rapid response capabilities and comprehensive characterization efforts. These collaboration systems provide models for future international cooperation in time-critical astronomical research. Database development initiatives create systematic repositories for interstellar object observations, analysis results, and theoretical models that enable long-term research programs and comparative studies while providing standardized data formats and analysis tools for the global research community. These database systems support systematic research while enabling efficient access to observational constraints and theoretical predictions. Educational applications of interstellar object research provide systematic opportunities for training next-generation astronomers, while engaging public interest in cosmic exploration and galactic astronomy through compelling examples of direct material exchange between stellar systems. These educational programs promote scientific literacy while supporting continued research interest and funding for interstellar object studies. Sample return mission concepts propose even more ambitious spacecraft programs designed to capture and return interstellar object materials for detailed laboratory analysis that could provide definitive compositional and isotopic characterization impossible through remote sensing techniques. These sample return missions represent ultimate goals for interstellar object research while requiring revolutionary advances in spacecraft technology and autonomous systems. Comparative analysis frameworks develop systematic methodologies for analyzing multiple interstellar objects, while identifying common characteristics and unique features that provide insights into formation mechanisms and galactic material transport processes. These comparative approaches enable systematic understanding of interstellar visitor populations, while providing statistical frameworks for theoretical model validation and development. Technological development priorities emerging from Through-Eye Atlas research include enhanced detector sensitivity, improved automated analysis algorithms, advanced propulsion systems for interception missions, and sophisticated computational modeling capabilities that address current limitations while enabling revolutionary advances in interstellar object characterization and understanding. Astrobiology integration opportunities arise through interstellar object research that could provide direct analysis of materials from other stellar systems, while offering insights into chemical conditions and formation processes that affect habitability and biological potential across galactic environments. These astrobiological applications connect interstellar object research with broader questions about life in the universe. Policy implications of interstellar object research include considerations of planetary protection, international space law, and scientific cooperation protocols that ensure responsible conduct of interstellar object studies, while maximizing scientific benefits and maintaining appropriate safety standards for spacecraft missions and material handling procedures. Funding priorities for future interstellar object research emphasize systematic survey capabilities, advanced characterization techniques, and ambitious space missions that require substantial international investment while providing revolutionary scientific returns through direct study of materials from other stellar systems and comprehensive understanding of galactic material exchange processes. Modern research integration combines interstellar object studies with broader astronomical research programs while providing systematic frameworks for understanding galactic evolution, planetary formation diversity, and cosmic material transport through interdisciplinary approaches that connect small-scale object analysis with large-scale astrophysical processes and theoretical frameworks. Tonight, every technological advance that improves astronomical detection capabilities, every international collaboration that coordinates scientific resources, Every systematic framework that guides future research carries forward the legacy of 3i Atlas and the revolutionary potential of interstellar object research to transform understanding of galactic evolution, while providing direct access to materials from distant stellar systems through patient observation and systematic study of cosmic visitors. Messages from deep space flow through the infinite quietude of interstellar medium, where objects like 3i Atlas serve as natural spacecraft that have travelled for millions of years across galactic distances, carrying with them the chemical signatures, physical characteristics, and formation histories of distant stellar systems that remain forever beyond the reach of human space exploration. These cosmic messengers drift through the vast emptiness between stars with patient persistence, their surfaces recording the slow accumulation of cosmic ray impacts, micrometeorite bombardment, and chemical processing that occurs during journeys spanning geological timescales across regions of space where matter exists in densities approaching perfect vacuum. In the deepest silence of cosmic time, where even the memory of stellar formation dissolves into thermal equilibrium, interstellar objects maintain their systematic migration through galactic space according to gravitational dynamics and stellar motions that operate with mathematical precision across scales that dwarf human comprehension. Every cosmic visitor carries forward the molecular legacy of its formation environment, preserving within its crystalline structure and surface composition the chemical fingerprints of nucleosynthesis processes, planetary formation conditions, and dynamical evolution that occurred around alien suns in stellar neighborhoods whose light may never reach Earth during the entirety of human civilization. The isotopic ratios preserved within 3i Atlas materials encode information about stellar evolution cycles, supernova enrichment events, and galactic chemical evolution that operated within distant stellar systems during epochs when our solar system remained a dispersed cloud of interstellar gas and dust. These chemical signatures persist through million-year journeys across interstellar space, their atomic arrangements maintaining evidence of nuclear processes and planetary formation chemistry that reflect the diversity of astrophysical conditions operating throughout the Milky Way galaxy's spiral arms and stellar populations. Contemporary spectroscopic analysis techniques can detect these ancient chemical messages through careful measurement of reflected and emitted light, where absorption features and elemental abundances reveal information about formation environments that may have operated under stellar conditions dramatically different from solar system chemistry. The same photons that enable astronomical observation carry across space the electromagnetic signatures of materials that formed around stars whose masses, ages, and galactic locations created planetary formation processes unlike those that produced Earth and its neighboring worlds. Gravitational dynamics that govern interstellar object trajectories operate through the same mathematical principles that organize galactic structure, stellar motions, and planetary system architecture, creating systematic connections between cosmic visitor kinematics and the large-scale gravitational environment of galactic space. The hyperbolic trajectories that prove interstellar origin also encode information about gravitational acceleration mechanisms, stellar encounter histories, and galactic velocity fields that affect material transport across the vast scales separating stellar systems. The technological capabilities developed for detecting and characterizing objects like 3i Atlas continue advancing human ability to receive and interpret these cosmic messages through systematic improvements in astronomical instrumentation, automated detection algorithms, and sophisticated analysis techniques that transform subtle brightness variations and spectral features into comprehensive understanding of distant worlds and alien formation processes. Future generations of interstellar object research will expand this cosmic communication network through enhanced detection sensitivity, extended observational capabilities, and potential spacecraft missions that could provide direct physical analysis of materials delivered from other stellar systems. These advancing capabilities promise to transform humanity's understanding of galactic evolution while establishing systematic frameworks for comparative planetology that extends across the entire observable galaxy. Educational applications of interstellar object research create opportunities for inspiring scientific curiosity about cosmic exploration and galactic astronomy, while demonstrating how systematic observation and mathematical analysis enable understanding of phenomena that operate across scales from molecular chemistry to galactic dynamics. These educational programs promote scientific literacy while encouraging future research into cosmic phenomena that connect Earth with the broader galactic community. International cooperation in interstellar object research demonstrates humanity's capacity for coordinated scientific exploration that transcends national boundaries while pursuing fundamental questions about cosmic evolution and the diversity of planetary formation processes operating throughout galactic space. These collaborative efforts provide models for systematic international cooperation in addressing scientific challenges that require global coordination and resource sharing. Theoretical understanding developed through interstellar object research advances human comprehension of galactic material exchange, stellar system evolution, and planetary formation diversity, while providing systematic frameworks for interpreting cosmic phenomena that operate beyond direct observational access. This theoretical knowledge enables humanity to participate intellectually in galactic-scale processes through mathematical analysis and scientific reasoning that connects local observations with universal physical principles. The patient orbital mechanics that carry interstellar visitors through solar system space operate according to conservation laws and gravitational principles that maintain cosmic order across scales spanning from atomic nuclei to galactic clusters, demonstrating the mathematical harmony that underlies cosmic evolution and enables systematic scientific understanding of natural phenomena across all scales of space and time. Technological legacy from interstellar object research continues advancing human capabilities for cosmic exploration while providing systematic approaches for understanding astronomical phenomena that operate beyond Earth's immediate cosmic neighborhood. These technological developments enable ongoing expansion of human scientific understanding while supporting continued exploration of cosmic mysteries that connect terrestrial experience with galactic-scale processes. Every careful observation of cosmic brightness variations, every systematic analysis that reveals material composition through reflected light, every mathematical calculation that determines celestial trajectories participates in humanity's ongoing conversation with the cosmos through scientific investigation that transforms electromagnetic radiation and gravitational dynamics into comprehensive understanding of cosmic evolution and galactic diversity. Rest now in the knowledge that cosmic messages continue arriving from distant stellar systems through patient interstellar travelers that carry information across galactic distances and geological timescales, their systematic delivery providing ongoing opportunities for scientific discovery and cosmic understanding that connect human experience with the broader galactic community through natural processes that operate with clockwork precision across the vast scales of space and time. Sleep peacefully in the certainty that systematic scientific investigation enables humanity to participate in cosmic evolution through careful observation and mathematical analysis. where patient study of cosmic visitors like 3i Attalus transforms brief observational opportunities into enduring scientific understanding that advances human knowledge about galactic diversity and the systematic processes that connect stellar systems across the immense scales of galactic space through natural material exchange operating over timescales that span geological epochs and stellar evolution cycles. The cosmic conversation continues through electromagnetic radiation and gravitational dynamics that carry information across interstellar distances with systematic precision, ensuring that humanity's scientific curiosity remains connected with galactic processes through ongoing opportunities for discovery and understanding that operate independently of human timescales, yet remain accessible through patient observation and systematic analysis of natural phenomena that bridge the gap between terrestrial experience and cosmic evolution.